Ich bin hier anstelle von Giorgio Benedekt, der sich herzlich entschuldigt, aber er war leider heute verhindert. Die heutige Sitzung behandelt das Thema des Mittelmeerraums als Bildung und Forschungsraum. Die Erweiterung des Bildungs- und Forschungsräumes zum Mittelmeer hin ist eine Grundlage für eine weitere Entwicklung und um den Austausch zwischen den Kulturen und eine bessere Zusammenarbeit zu fördern. So, heute haben wir 4 Vortragsredner und wir beginnen mit Amos Bertolacci, der spricht über das Thema Arabic, Persian, Hebrew Science in Medieval Latin Europe.
Thank you very much. Una parola di ringraziamento sentito per Loris e Alessandra per aver organizzato il convegno e per avermi invitato. Di fronte al dilemma se parlare in italiano trovandoci in Italia o in tedesco trovandoci in un contesto Humboldt, ho scelto una via diciamo aristotelica, una via di mezzo e parlerò quindi in inglese. E Aristotele ci dà un po' il contesto ecco, del discorso che andiamo a fare. Mi sentite in fondo? Ancora di più? Sì, perfetto. Lasciamo stare. Va bene, grazie. The Mediterranean Sea has always been a space of confrontation on the one hand and dialogue on the other, or, as in the title of our conference, of conflicts as well of chances. This is certainly true of the Middle Ages, the historical period I am going to touch in this paper. The medieval Mare Nostrum is crossed by lines of fiery competition on the religious, political and military side, but also by trends of fruitful interaction on the economic, commercial and cultural side. Let us think, by way of examples, of Louis IX of France, St. Louis, promoter of the 7th and 8th Crusade, and as in his counterpart of Frederick II of Swabia, the poor Apulie, patron of culture coming from non-Christian lands in his court in Sicily. Let us also compare the route leading pilgrims to Santiago de Compostela in Portugal in order to venerate Saint Jacob, killer of the Moors, Matamoros, with Toledo, the Spanish city in which, after the Reconquista, Christian, Muslim and Jewish scholars cooperate to investigate and translate the common cultural heritage. The examples could be multiplied. Some events which took place in the Middle Ages bring us back to the most recent and dramatic actuality. Pope Innocent IV in 1245 sent 4 delegations to various Mongol kings in order to establish a non-aggression pact. These diplomatic contacts shaped a sort of international coalition ranging from the west to the far east against the Islamic caliphate of the time. In 1256, 2 Dominican friars were decapitated in the Holy Land by the Saraceni, the name by means of which Muslims were usually called. 5 further Dominicans were executed in 1268 in Antiochia of Syria, when the city fell under Muslim control. And it is well known that pirates in the Mediterranean put in danger not only strategic locations or material goods, but also personal human freedom, since many Europeans were captured by them and brought as slaves on their ships towards the harbors from which the immigrants of nowadays depart in order to find fortune in the old continent, with the risks and tragedies that are part of our daily news. Nothing is new under the sun, therefore, especially the sun that shines over the Mediterranean shores. But in front of this political emergency and the related military confrontation, medieval Europe found in culture a bridge capable of overcoming the danger of a clash of civilizations. The present paper deals with this positive pole of the issue, that of dialogue, interaction, and chance, without ignoring the opposite negative pole. The field of investigation is potentially endless, as you understand, and I cannot but proceed by way of examples. In Latin medieval Europe, we are lucky enough to encounter a figure like Albert the Great, Albertus Magnus, who died in 1280. This bishop, theologian, and philosopher got the epithet of Doctor Universalis because of the vastness of his theological and philosophical production, whereas his pioneering scientific interests earned him the ecclesiastic role of patron of scientists in 1941. Albert the Great, profound knower of all the theological, philosophical, and scientific sources available at his times, is therefore the best representative of his epoch about the issue we are discussing. In order to establish a channel of communication with Arabic culture, the general strategy envisaged by Albert the Great was to place a clear-cut divide between religion, with all its political implications on the one hand, and philosophy and theology on the other. The religious texts of Islam and Judaism, although translated into Latin, were known indirectly to Albert, as they were to many of his contemporaries, mostly by means of polemical summaries in order to be sharply criticized and rejected. Philosophical and scientific texts, on the other hand, written in Arabic by Muslim, Jews, and Persians, on the other hand, were inspected directly and really perused by him in order to be digested and transferred into his own philosophical and theological works. In the conclusion, we will consider whether the approach as exemplified by Albert is still viable nowadays, and if it is, on which grounds. But before we enter in medias res, each of the three elements of the title of the paper needs to be clarified. First, the Arabic language, meant as the lingua franca of scientific communication in the Middle East after the rise and success of Islam, served as a collector of different cultures and was adopted also by scholars belonging to non-Arab ethnicities like the Persians and the religions different from Islam like Judaism. In this way, if we consider the linguistic setting, we can merge Arabic, Persian, and Hebrew science into a single folder. Few relevant works written by Persian or Hebrew authors of the time were composed in their own native tongues rather than in Arabic, and very few of these non-Arabic works were translated into Latin. In other words, the translation movement from Arabic into Latin that took place from the 10th until the beginning of the 13th century conveyed the essentials not only of Arabic science, stricto sensu, but also of Persian and Hebrew science. To use Loris Turlese's expression, Arabic was the third language of philosophy, besides Greek and Latin. Second, when speaking of science in the Middle Ages, we must be ready to adopt a broad notion of this concept, which certainly encompasses the exact sciences, but which sets science, in this narrow sense, into a larger and very integrated system of knowledge. In this system, logic, philosophy of nature, mathematics, and metaphysics are sciences at the same level and with the same rights and prerogatives. And to these general branches of knowledge, more particular applied sciences like algebra, optics, mechanics, medicine, and so forth are subordinated. In other words, in medieval times, the boundaries between scientific and humanistic disciplines are very fluid, and science is not sharply distinguished from philosophy. On the contrary, science is an integral part of philosophy, whereas philosophy provides, in some cases, the general context, and in some other cases, the foundation of what we currently mean by science. Third, from the chronological point of view, only in the 13th century the Latin translation of a large portion of the Arabic cultural heritage with its Hebrew and Persian accretions was completed and became available in its full extent to European scholars. And let us start with Albert the Great now. On 15 May 1248, in the capacity of professor of theology at the University of Paris, Albert signed, together with other colleagues, an official document in which the Talmud, the Jewish commentary on the Bible, was condemned. The document in question was the result of the doctrinal exam supervised by the Bishop of Paris, and the condemnation was solicited by the King of France, the already mentioned Louis IX. This episode falls at the end of Albert's Parisian teaching because in 1248 he moved to Cologne in order to become there the regent master, the director, we could say, of the newly founded studium of the Dominican order. We do not know anything about the degree of Albert's involvement in the condemnation of the Talmud, and we do not know the effects of the decree. In particular, whether the Talmud was publicly burned after the condemnation of 1248, as it was after the previous condemnation of 1240. It is, however, certain that this condemnation had no repercussion on Albert's philosophical activity, since in the commentaries on Aristotle that he started writing in Cologne, many Jewish philosophers, like Maimonides, Isaac Israeli, and others, are frequently mentioned and positively exploited. Even more significant is another event of Albert's life, which happened about 15 years later. In 1263-64, Albert preached a crusade in the German-speaking countries upon the order of Pope Urban IV, who, for this reason, relieved Albert from the duties of Bishop of Regensburg. The projected crusade never took place because the Pope died in 1264, and also Albert's preaching consequently ended. We do not know the content of Albert's preaching, but we can imagine that he used some anti-Islamic motifs current in medieval Latin culture regarding both the theological positions and the moral customs of Islam. These motifs are similar to the attack against the Lex Mahumeti, which he makes in the commentary on Aristotle's Nicomachean Ethics, written a few years before, and against Muhammad himself as master of falsity and baseness, which he makes in the commentary on the Politics some time after. This polemic is in a way traditional. In the first case, for example, Albert is inspired by the Byzantine commentator of Aristotle's Nicomachean Ethics, Eustratius of Nicaea. Likewise, the polemic is restricted to the practical dimension of ethics and politics. By contrast, immediately afterwards, between 1264 and 1267, Albert wrote his commentary on Aristotle's Metaphysics. And you find in this table a conspectus of authors or works quoted by name or by title by Albert in the commentary on the Metaphysics. In the table, the scientists are evidenced in red. They are mathematicians like Euclid, physicians like Hippocrates, astronomers like Ptolemy, Albitrugi, Thabit ibn Qurra. In green are evidenced the Greek authors quoted by Albert indirectly through Arabic sources, like John Philoponus and Themistius. In general, we can see that after the ancient Greek authors, the Muslim authors writing in Arabic are the most numerous authorities mentioned by Albert. Some of these Muslim authors, as Ghazali and Avicenna, are Persians. Others, as Farabi, are Turks. Still others, as Averroes, Albitrugi, and Ibn Bajjah, are Andalusians. Two of them in particular, Averroes and Avicenna, the authors of the two major treatments of metaphysics in Arabic, are the auctoritates most frequently quoted after Aristotle and Plato in the commentary. Significantly, the Arabic sources quoted by Albert are more numerous than the Latin sources, as you can see, among whom some names, like that of Augustinus, are strikingly absent. Because of this massive use of Arabic sources, Albert's commentary on the metaphysics is unprecedented in Latin philosophy. And some general lessons can be derived. First, the idea of burning the books of the Jews or of waging a war against the Muslims is totally alien on the cultural side to Albert as a theologian and a philosopher. The commentary on the metaphysics, like all other Aristotelian commentaries of Albert, as well as his previous and later theological works, contain frequent references to a wide array of Muslim and Jewish philosophers and astronomers, foremost among whom, as we have seen, are Avicenna and Averroes. Second, Albert, as a man of church that obeys the bishop's intention of condemning the Talmud or the Pope's order of waging a war against the Muslim infidels, but as a scholar, he uses abundantly in his works Arabic writings of Muslim and Jewish authors. In this way, Albert well exemplifies the two-faced attitude of the Western medieval world towards Islam and Judaism, clash of religions on the one hand, positive dialogue in the field of culture and in the perspective of the common Greek heritage on the other. Third, Albert comments on the metaphysics according on a translation of Aristotle's text made from Greek, but at the same time depends massively on Averroes and Avicenna, known by means of Arabic-Latin translation, for the interpretation of Aristotle's work. In this way, Albert provides a glaring example of how unhistorical is any attempt to create a fictive divide and opposition between the process of transmission of Aristotle's works from Greek into Latin and the concomitant tendency of interpreting the Aristotelian litera with the help of the exegesis developed in the Arabic-Islamic philosophical context. Sylvain Guggenheim, in a recent book, notoriously holds the opposite view. The commentary on the metaphysics was part of Albert's overall project of divulgating philosophy to Latin readers by explaining each of the works belonging to the corpus of writing transmitted under Aristotle's name, enlarged with other traditional works and completed by Albertus himself, a project whose realization took about 20 years, from 1250 until 1270. In the first of these commentaries, the commentary on the physics, Albert programmatically declares his intention to make the three essential parts of theoretical philosophy, namely natural philosophy, mathematics, and metaphysics, intelligible to Latin readers. And you find the text in the third point of the slide. Albert says, since the essential parts of philosophy regarding things are three, namely natural philosophy or physics, metaphysics, and mathematics, our aim is to make intelligible to Latin readers all the aforementioned parts. In scholarship, starting with Pierre Mandonnet in 1899, if not before, this declaration is often reported as Albertus' intention of remaking Aristotle to the benefit of Latin scholars or making Aristotle intelligible to Latins. This scholarly topos is misleading in a double respect, since it does not mirror faithfully Albert's text, and since it disguises another fundamental aspect of Albert's Aristotelian commentaries, namely the aim to report in an objective way the position of the Aristotelian school, namely the Peripatetics, rather than Aristotle alone. And we can see a statement like this in the commentary on the metaphysics. But all these things are easy to determine if the positions of the peripatetics, whose opinion we explain here, are kept in mind. And the evidence in this regard is very abundant, as you can see in this slide. From a statement like this, it is evident that Albert's aim in the Aristotelian commentaries is wider than a bare exposition of Aristotle's view and encompasses also the doctrine of his disciples and followers, the peripatetics. This enlargement of the scope from Aristotle to the peripatetics is very important for our topic. Because among the peripatetics, more precisely among the later peripatetics, the peripatetici novi or posteriores, Muslims and Jews play a fundamental role. Let's say the texts in the slide. Albert says, left aside the works of some modern thinkers, we will follow only the opinions of the peripatetics, and especially of Avicenna, Verroes, Al-Farabi, and Al-Ghazali, whose books on this issue we found in mutual agreement. And if we switch to the last text in this table, but this opinion about the nature of time is that of the Arabs, although many Latin thinkers are of different advice. Elsewhere, following the Latins, I might have said and written something different, but here I propose to follow the Arabs in everything, since I believe that their understanding of time is true. This being the case, it is not surprising that in the Aristotelian commentaries, Albert underscores the consistency of this layer of peripatetic philosophy and of peripatetic philosophy in general. Conversely, a certain animosity that Albert shows against some Latini and their aberrationes can be explained as an attempt to defend the position of the peripatetici, especially of the peripatetici posteriores, ignored or rejected by the Latini. Thus, the exposition of Arabic and Hebrew philosophy is an integral part of Albert's exegetical project regarding the commentary on Aristotle and, more in general, his school. In this perspective, we can say that Albert's commentaries are, at the same time, exposition of Aristotle's thought, but also, by the same token, accounts of Arabic and Hebrew Aristotelian philosophy. Albert allows himself full doctrinal freedom in expounding the views of Aristotle and the peripatetics by means of the so-called disclaimers, namely by means of frequent contentions, widespread in the Aristotelian commentaries, of being simply an expositor of alien views on sensible doctrinal points. In other words, through the disclaimers, Albert excludes any personal involvement in the doctrines of the Aristotelian commentaries in case of possible conflict with the theological truth. And in this way, he considers himself entitled to expound the philosophical views as they are, i.e. within their context and according to a purely rational method. In the slide you have a selection of disclaimers occurring in the commentary on the metaphysics. Albert says in the first text, let us end this discussion in which I didn't say anything according to my own opinion, but everything was said according to the positions of the peripatetics. He who wants to ascertain this must read attentively their books without praising or blaming me, but them. And the other two passages are of similar content. Elsewhere, Albertus draws a distinction between the approach of the philosophy and that of the sancti to disputed issues, and between the fields and methods of philosophy on the one hand and theology on the other. Future research will assess whether this delimitation of boundaries is absolute and waterproof, as in the coeval Faculty of Arts at the University of Paris, or whether it entails a certain amount of synthesis between philosophy and theology. But leaving this issue aside, what is important now to stress is that the disclaimers are linked with Arabic philosophy in a double respect. On the one hand, they allow to Albert a free exposition of falsafa within the Aristotelian commentaries, as we have seen. On the other hand, they seem to depend methodologically from two Arabic philosophers, Avicenna and Averroes. Avicenna envisages a double epistemic route to what he calls in this text the return of the soul, namely the eschatological destiny of the human rational soul. There is the route traced by religious law and prophetic revelation regarding the material and sensible happiness and misery in the afterlife, in the first paragraph. But there is also the route marked by pure reasons and demonstration regarding the bliss of the intellectual part of the soul after the separation from the body. And this is the kind of reward that the metaphysician aspires to. Likewise, Averroes, in his commentary on the metaphysics, takes the study of reality in its entirety proper to the philosophers to be the law and the cult most noble and appreciated by God. And sorry for the Italian translation, but the relevant passage is the one underlined in bold. The law, Sharia, so this is a term with an intense meaning, proper of the wise man, in fact, is the investigation of the existence in their totality. So philosophy, we can say, is the cult that the metaphysicians pay to God. Albert could not read this passage of Averroes' long commentary on the metaphysics since the Latin translation omits this passage. But in the same commentary by Averroes, he could read several other passages of this kind in which a clear-cut methodological distinction between the provinces of philosophy on the one hand and the religion and theology on the other is posited. I'm going to conclude. Michael Borgolt, in an article of 2011, aptly speaks of an labiles Gleichgewicht zwischen Religionen und Kulturen in the Middle Ages. Albert the Great provides a glaring example of this unstable balance. He closes the door, so to say, to dogmatic discussion and confrontation at the level of religion, regarding Islam as a religion unworthy to be compared to Christianity, but he opens the gate of cultural reception towards Muslim thinkers, insofar as these same Muslim thinkers, like Avicenna and Averroes, establish a rigid distinction between the realms of reasons and philosophy on the one hand, and of faith and revelation on the other. Albert's approach, or the influence of his sources, is epoch-making. If it is true that an attitude not very different can be found in Dante Alighieri, in the Commedia, the prophet Muhammad and his nephew and son-in-law Ali are posited in hell, whereas Avicenna, Averroes and Saladin are placed in the noble castle of the limb, together with the other spiriti magni of antiquity. Let us conclusively ask, although Albert's reception of Arabic philosophy is never passive, but always attentive, critical, and selective, is it simply an instance of cultural transfer, or can be taken as a real case of cultural dialogue? In the second case, can it provide some indication on how to create a cultural interlocution between opposite religious systems even nowadays? The relevant questions in this regard seem to be three. One concerns the object of discussion, the other two, the referent and the actor of the dialogue. Whether some themes of interreligious interest can be found in contemporary emergencies, like ecology, bioethics, human rights, and so forth, an answer to the following two questions, with whom and by whom, looks more difficult to find. I thank you very much for your attention.
Grazie molte, abbiamo tempo per qualche domanda.
Italiano o inglese?
Italiano.
Una domanda brevissima su questa trasparenza su autori elencati, l'elenco di autori citati da... che cosa, colore rosso, cosa significa?
Ma significa che questi sono gli scienziati. Quindi abbiamo Euclide, Ippocrate. Sì.
E l'altro invece un pochino più lungo?
Quelli verdi, diciamo, sono gli autori greci, ma conosciuti da Alberto grazie a fonti arabe.
Invece l'altro potrebbe dire qualche parola, elucidazione sul natura di tempo, nature of time according to Arab.
Ah, sì. Lì è il conflitto tra la visione agostiniana del tempo e quella filosofica, quindi tra la visione del tempo come un fenomeno legato all'anima, come in Sant'Agostino, e la visione del tempo invece come la misura del movimento, come prima di tutto in Aristotele e poi nella tradizione aristotelica araba. E in un'opera teologica come quella che abbiamo visto, Alberto Magno non ha esitazione a mettere da parte momentaneamente, in quel caso Agostino, e ad abbracciare, diciamo, la prospettiva araba sul...
Thank you very much. It was very interesting and important. I would just like to mention, to pinpoint that we should at least mention and stress the role played by Syriac, both as a language and the Syriac-speaking peoples, that is the Eastern Christians, both in the passing over of Greek philosophy to the Arab world, to the Muslim world, and backwards from the Muslim world to Europe. I mean, without really the Eastern Christians, without Syriac as a medium, we wouldn't have had any.
Absolutely. No, you are absolutely right, and many works were translated from Greek into Arabic, but through a Syriac intermediate stage, so this is definitely important. On the other hand, Albert did not enter into contact directly with the Syriac authors or sources, but you are perfectly right about the historical importance of the Syriac.
Sì, posso in italiano?
Sì, volentieri.
Grazie per la ricchissima illustrazione del background arabo. Io sono convinto che la seconda soluzione a cui accennavi, cioè quella di un reale dialogo nel caso di Alberto Magno, per quel pochissimo che, insomma, per quel zero che ne so, possa essere la via migliore per questa relazione. Però volevo solo, diciamo, sollevare un problema su un piccolissimo punto minore. Tu giustamente hai detto che la presenza rispetto alla trattazione della metafisica è soprattutto di autori greci filtrati attraverso gli arabi o direttamente dei peripatetici tardi, che poi sono tutti arabi sostanzialmente. E hai giustamente detto che manca strikingly Agostino. Secondo me non è tanto strikingly e soprattutto non è strikingly perché nella tradizione latina Boezio, che era stato il grande mediatore, si è completamente dimenticato sia la parte metafisica sia la parte fisica, si è concentrato su tante altre cose, ci ha lasciato le categorie, ha fatto cose meravigliose, però fisica e metafisica non sono state decisamente, come dire, i suoi terreni preferiti. Quindi credo che questa assenza potesse essere colmata rispetto al mondo latino solo tramite gli arabi, non c'erano veramente altre strade, non so che cosa ne pensi.
No, guarda, d'accordissimo, se vedete nella colonna di centrale, no, delle citazioni degli autori latini, Boezio in seconda posizione, 9 citazioni, è l'autore citato più frequentemente ovviamente da Alberto nel commento alla metafisica. E ecco, da questo punto di vista, diciamo così, Alberto segue una tradizione. Ecco, l'assenza di Agostino, hai ragione, non è poi così striking, ecco, in questo caso, diciamo così, è più forse il contesto generale, no, di un nuovo tipo, ecco, sì. Ma ti ringrazio molto e sono d'accordo.
In one of your transparencies about Averroes, you list a word which is today politically very charged, the Sharia. So I just wonder whether the context here is different, because it seems to be it's a law of the wise men rather than the law that comes out from the Quran. So is that the same thing?
There are two other terms, let me see if I can, which are...
the Shar and then the Sharia.
Yes, the Sharia is here.
But that's the
there
word
are two other very, very religiously charged words, which are Inaya, the cure, or which is also the divine providence, and the Hida, the Shark and Hida, which are the explanation, which is also a religious term used in order to explain the Quran, etc.
So this law is the same one that comes
absolutely.
out of the Quran.
I have the impression that Averroes wants just to make a distinction similar to that of Avicenna. So there is a philosophical law which is sufficient to gain salvation for the philosophers, and this is just the practice of philosophy, especially of Aristotelian philosophy. And then there is the law for common people, which is the law established by the Quran. Yes. Which is established in a sensible way with sensible images, just because it addresses a wider public. But the philosophers, according to Averroes and Avicenna before him, have the capacity of getting to the real truth of what really God wants as a law to be followed by humans. So
given the current applications of the word Sharia around the world, certainly got distorted through the centuries.
Yes.
Because they're certainly not what these people were writing 600 years ago.
Yes. No, you are right. And the context is that of the explanation of a passage of Aristotle's Metaphysics, in which Aristotle himself says that laws or practices have influence on human education and human understanding. But I think that in an author like Averroes, who was also a theologian and a qadi, a judge, the employment of the term Sharia cannot be accidental in this case. I think he wants just to separate two kinds of laws, a higher law for philosophers and a lower law for common people.
Grazie molto, allora direi di passare alla prossima relazione. Che di Francesco Gianturco, che ci parlerà the dawn of chemistry, the making of early universe molecules.
Full screen, dove si mette il tape. Questo non mi sembra lo stesso formato che conosco io, non è lo stesso che conosco io, quindi dove si mette il full screen. Okay, finally. Okay, so I hope you heard what I said at the beginning, so I won't go to repeat it. But I want to thank the organizers. I'm glad the microphone works, because they've been very kind and very effective. And so far, the meeting has gone very well, and I'm sure there was a lot of work behind it. So thank you very much for making this possible and bringing us all here. So what I'll try to do, though, today is to talk about something which is connected with the theme of the meeting. And in spite of the fact that what you see here is a general title about the dawn of chemistry. And what you see, this is a composition of all various constellations and various stages of the formation of planetary structures. So I won't give you the list, but in case you want to look into any of the Wikipedia database, you will find that all of these correspond to different stages where you have actually been signs and evidence of formation of chemistry. Why I'm talking about molecules? Well, we should be moving. Yes. So the reason why I mention that is because we want to understand really what happened to the origin of molecules at the beginning of the universe. And the reason why this is interesting, partly for the meeting, is because accidentally, in a sense, the work that goes into producing this type of information connects many types of different scientists. But a lot of the recent modern work has been done in the Mediterranean areas by centers in Rome and Florence. And interestingly enough, in Florence, it was just done in places where Galileo used to live. So Arcetri was one of the centers where some of the early universe studies were done. So in a sense, it is a Mediterranean enterprise, in spite of the fact that so many different people have been working on it. Now, the main reason why we are looking at molecules are listed here. In other words, we really want to know why there are molecules in this acronym that you'll be seeing most of the time, which is called the interstellar medium, the ISM. There are lots of molecules, and in a moment I'll give you examples of why and where these molecules are. So they are actually, we've discovered that they are very important in guiding the evolutions of the stars into the planetary formations. So we need molecules because they will work as the micro-refrigerators to help the system to actually cool to the conditions that, for instance, we have in our planetary system near to our dear star, the Sun. And of course, and the reason why I'm mentioning them now is because they are very few and very simple molecules, but they still played a role in the development of the early universe. So, if we want to look at another ways of presenting what I'm talking about, is that if we want to imagine that in our universe there have been an evolution of chemistry into the complex systems and reactions that we have on our Earth, this goes contemporary and parallel to the development of the structures of the stars into the planetary system. So knowing molecules in the prestellar cores can give us some indication of how we will finally get to the complicated systems that we have on Earth, and also all the various things that have been found in various solar systems. Remember that the evidence seems to be now that there are more than 2,000 planetary systems which have similar temperature conditions, not so much more than that, but similar to the one we are in. So molecules are everywhere, and the molecules are really very important for getting us where we are. So, but what do we see now in our present universe? We see that there are at least 300 different types of molecules, and in fact, some of these molecules are very relevant to the prebiotic stage. So the people who spend their time working in what is called bioastrophysics, or biological sources in the universe, are in fact very keen in discovering that some of the molecules that we know on Earth as being amino acids or larger molecules have been in fact observed around us. But another interesting thing is that some of these molecules don't really have the structures that we know on Earth. Some of these molecules would not be stable on Earth. So obviously the chemical cooking that takes place in the universe is not exactly the same that takes place on Earth. Now I see that I move the microphone. Can you hear me even when it's far away, or it's confusing even more? So one thing that unfortunately tell us that we are really looking at very tiny fractions of our universe is to describe what today's cosmology recognizes as the composition of our universe. And now, I'm sorry you can't see the number here, but this is about 75. So we have something like 95% of our universe that is made up of dark energy and dark matter. And this is in fact one of the puzzles today of the unification in scientific knowledge, to discover why do we have this sort of very obscure terminology related to some form of energy that we don't really know, and certainly some form of matter that affects the gravitational pulls, but we don't really know what it's done. But the bottom line is then that 4% is really hydrogen and helium. So most of whatever goes into the general terms of baryons. I'm moving my accent the wrong way. So the baryons are in fact mostly made up of hydrogen and helium. And all the molecular things that if you exclude neutrinos, most of the molecular things that we are talking about is really something like 3%. So this complexity of the molecular world and the origin of the molecular world is really involved in a very tiny part of the largest compositions of the universe. So really just to humble ourselves, we are sitting somewhere in one of these sort of another mapping of the cosmos in terms of the putting the baryons then in the yellow region, and all the rest is really dark matter, and the voids where there should be the essence of the dark energy. So somewhere in these little spots we exist. So the question is really, how do we manage to study and understand what happens in our early stages, and why are the molecules important? Well, the first thing we have to see, how do we go back in time in our universe studies? And one way of going back in time is really looking at the dark regions of our stars. So if we look at the fainter sources, and this with our mighty greatest telescopes of today, we are really able to try and see that in spite of the presence of so many lights, there are very dark spots where possibly very faint sources will be able to tell us something about our universe. And this was in fact the rationale behind building so many of the satellites and probes that went out to look at the farther away regions of our cosmos. And why do they have to be far away? Because the farther they are, the older they are. So we know, in fact, that by looking at these very faint lights, we are actually looking at light that has traveled a long distance and has started a long time ago in order to get to us. So our only way of talking to the universe is really by looking at the light that comes from the various parts of it. Tomorrow we'll have another conference on light and the measuring of time, and in a sense astrophysics has already done over the years by, in a macroscopic sense, measuring time through the examination of light. For instance, we all know that if you're looking, I left the terminology in Italian because there is also Italian as the language of this meeting, so I might as well not translate terms like sun and earth. But you probably know that whenever we see light from our sun, we know that left the sun 8 minutes ago. So it's at least 8 minutes old whenever we actually see it. Now, if we get a bit more complicated and we look at one of the galaxies which are far from us but not so far, we actually find that the Andromeda galaxy produces signals that have left the galaxy about 2 million years ago. So the photons that come to us are at least 2 million years old. But they seem to be in good health because we managed to see some of the signals. And we can go even beyond, and this is one of these this is another of the acronyms. Astrophysics is full of acronyms, and this is one related to one of the stellar objects. So it's a quasi-stellar object. So it's not yet a star, and yet it's emitting light, and one can reckon that this happens 1,000 million years ago. So 1,000 million years, the life led the QSO, which has now been recognized as a later developing into a star object, and reached us. So what we really see from this, that by looking at signals which come from a long way away from where we are now, we are really doing some sort of archaeology of the galaxies under our universe. There is a problem with this because we already know through the Big Bang theory that this universe is all moving, is continuously moving, which means that it certainly moved from the beginning, which means that we have a problem with looking at a moving object that emits light. So these indicators of early universe structures, which are the signals coming from the early universe, are moving away from us, and at the same time something happens to the light. And this is what is known as the redshift. And this is something which is very important to us to understand how we date the light that reaches us from this object. So, well, we all know a light is really associated with some sort of wavelength. So you know that the blue light has got a shorter wavelength and the red light is a bit longer. And if you have objects that move away in time, like these two little spots here, the light that they emit from one another or to one another is in fact changing its wavelength because the objects are moving. So because these objects are moving and they were closer a long time ago compared to now, we expect that the wavelength of the light that they were emitting is in fact moved into the infrared to much larger wavelengths. So the universal redshift is really caused by the fact that the galaxies are moving away from us, and by emitting light, we have to adjust the measurement. So light comes at a different wavelength, and it tells us something about the age of the object from which it started originally. So the redshift is really simply what is called a Doppler effect. This is known from 19th century physics. You have a moving source, and that creates a redshift. But this, of course, gets transformed into the cosmological structure by the law that was due to Hubble, which means that, in fact, the redshift gives us a measure of how far in time this object produced the light. So it links wavelengths with the cosmological constant and with the velocity of light. So the redshift is an indicator of an old source of the light. So if you're looking at the early universe, then Z must be very large. And today we live in a Z equals 0 universe. So if we do our counting and we look at the galaxies moving and the different sources, we can come up with an answer to what it say, how old is our universe? Now, I'm not answering the question, what happened before our universe was born. I'm just telling you that the astrophysicists just managed to measure the age of the universe through this triangulation system of different light sources and came up with a suggestion, which is the answer that we have now, verified by many different experiments, that our universe is 14 billion years ago, was when the Big Bang occurred. So the early universe is something very close to the Big Bang, something which happened more or less 300,000 years after the Big Bang. So one interesting thing is therefore temperature. These objects were very hot when they existed, but some of the newer objects are still hot. So for instance, this is a picture of our sun. How do we know its temperature? And again, temperature comes through the examination of the light. So if you look at a map of the different light sources from the sun, you can decide that the temperature of the sun on average is 5,000 centigrades. And it came to us 8 minutes ago. But if you look at the faint light that comes to us now but really traveled from 14 billion years ago, the wavelength that you find now is that the temperature of this faint light is 3 centigrades. So we are really looking about very large differences in temperature which are related to difference in age. So our star will get colder with time, but I don't think we need to worry about it. Not anyone in this audience. So in fact, how accurate this information are, it's very interesting that one of the ways physicists look at temperature is by looking at a black body, which is a model of a homogeneous source of light. And it's interesting to see that if you do a mapping of the solar emission, which is this red quantity here, so these are observations at various wavelengths of the light emitted by the sun, and then you use a model in which you say that the temperature should be 5,780 Kelvin, and you find that it fits almost perfectly this distribution. So we now have tools that we can look at light sources and define their temperature, hence defining the age of the object in terms of when the light was emitted first. So this is in fact the light emitted by what is called the microwave background radiation. So the reason the whole universe measured by several observations over the last period. This project, the FIRAS, was a project that managed to measure the black body radiation in the universe, and everywhere this is 2.72 Kelvin, and it fits very well the black body radiation. This is very important because it tells us the remnants of objects that were in fact very close to each other at a much higher temperature is now distribution of this very faint source of energy, if you like, but also source of light in the universe. And small deviations of these distributions are also used today by cosmologists to understand what happens at the beginning of what problems we have. But we still have not talked about molecules. So let's go back to molecule, and this is related to the great, what I call here the two opposite effects of the Big Bang. You have an expanding universe, which is described here at the beginning, very hot and blowing apart, but at the same time, we know that gravitational forces are pulling it back. So the development of universe and parts of the universe is really due to these two great effects. Explosion after the Big Bang, cooling that has to occur during the gravitational pulls. Because in fact, if the cooling doesn't occur, the object explodes again. And so here you have the effect of another explosion indicating that a bigger, hotter object becomes smaller, still hot. So in other words, stars are formed by this interaction of these two expanding universe forces. So this is another picture of it. You have a very hot core, and you have this, what is called a hydrostatic balance between the gravitational pull and the explosion, and inevitably this core will break up in different parts, which become smaller and smaller, and then there will be stars, and what around the stars? The planetary draft. So you have an expansion in this is a region where there are, as you can see, there are several stars that have been formed after the original expansion. And what you have is, this is also one of the galaxies away from us, where you're actually forming this spiral structure where different temperatures indicate different stages of star formation. So stars, in order to be formed, need to cool in the process of the explosion. So the cooling of the universe is an important feature for discovering how far and how small the parts will be. This is, in fact, the traditional formation of the planets. You've got a star here. You have an explosion that has produced a lot of smaller fragments that will eventually cool down, and they will distribute themselves around this accretion floor, around this disk structure. So if you like, all the planetary systems are really this debris formed away from the star and kept there by the relative attraction and by the reduction of the temperature after the explosion. So we are sitting somewhere in one of these little debris here, and the question we want to answer is why and how is the system cooling? Because to explode is not enough to produce a cooling without further fragmentation. So the early models, or after the Big Bang, are really doing some information about atoms that form this universe, and the atoms are really very simple, only hydrogen and helium. The first attempt at looking at something different on the periodic table is the presence of lithium. So here we are. The original soup of the early universe only involves 4 atoms: hydrogen, helium, and the isotopes, and lithium. But look at the quantities that have been estimated. There is a lot of helium with respect to the hydrogen, which is the dominant abundance, but all the others are really present in very small amount. So lithium atoms compared with the hydrogen atoms, they are different by 10 orders of magnitude. So here again, the chemistry we are talking about is a chemistry that involves very tiny parts of our universe. And so the cosmological cycle goes through 2 different processes. The collisional heating, because during the explosions, these heavy particles collide with each other, they fragment again, and they transfer internal energy, and then they have to lose this energy. And the most efficient way of losing this energy is by radiative cooling. So objects explode, they get hot during the explosion, and as they move away, they have to cool. Not only kinematically, not only slowing down, but also emitting radiation. And the problem is then that this is the cycle. With collision, you're actually going up, you are producing some sort of excitation. Now what is this panel doing? Okay. With collisions, you're going up, and then the radiation has to be emitted. So these are the 2 cycles of the growth of the universe. A collisional transfer that heats up the various parts, and then these various parts have to emit this internal heating by radiation. But there is a problem here, that as you move further away and you're actually slowing down, you may not be able to transfer this energy to the internal degrees of freedom. In other words, atoms are not sufficient. And why are not sufficient? Because in the atoms, in the light atoms that we've been talking about, the internal levels are very far apart. So as the temperature decreases, you cannot really transfer energy internally to the atoms. So you need molecules. The molecules have internal distribution of energies, if you like. The number of levels are much more dense than in the atoms. So as the system grows and slows down, the collisions will need molecules, because those will be the ones which absorb the energy and can emit the photon. So the bottom line really is that we need molecules, because these molecules will be responsible ultimately for cooling the early universe. These are some numbers. I don't know if you can read them, and it's not terribly important. So if you're cooling by thinking only the hydrogen atoms, then if you go to a temperature below 10 to the 5 Kelvin, so 100,000 Kelvin, the hydrogen cannot be excited anymore, and therefore you need something which has a structure of levels which are closer. And here we are the molecules, and you can see some of these molecules, lithium hydride, H2+, all these molecules will cool down to a few Kelvin. So as the system cools down, you need the molecule to transfer away the energy by radiation. Now, let me check how long I've been talking, probably already a long time. So I probably could get down to my bottom line here, which is reported a few hundred transparencies later, and so I will show them here. And the chemistry then involves essentially hydrogen. So what is the chemistry of the early universe? Hydrogen molecule formation. And I cannot tell you, of course, some of the details, but it doesn't really matter. What matters instead is that you see here some of the projectiles which make chemistry in the universe, the photon and the electron. So this is a different chemistry of the early universe. The photons are there because the stars have ionized hydrogen and helium, and therefore you have electrons. So a lot of the chemistry of the early universe is a chemistry that involves electrons and photons. And on Earth, photochemistry is partly important for the biological problems, but a lot of does not involve electrons. So the formation of these early molecules, and this is another example, the molecules that are formed, lithium hydride ions. As you can see, these are diatomic molecules. At the most, they can put together 2 atoms. And one of the reasons was in one of the many transparencies that I didn't show you, is that if you imagine the molecules in this room, the air, whatever other we have added to the air, they bump into each other sometimes like 10 to the 8th times per second. Now, in the interstellar medium, they hit each other with 15 times more, less frequently. So let's say a collision every couple of weeks compared with a collision every 10 to the minus 8 seconds in this room. As a result of it, then molecules don't really bump into each other very often. They have to emit radiation. That's why all these reactions are really reactions that will destroy the molecules, and they will destroy the molecule by photodissociation. So these are other possible reactions, but again, they involve only 4 different atoms: helium, the hydrogen atom, the lithium atom, and that's it, and their corresponding ions. So the entire chemistry of the early universe, let me show you the bottom line. Well, I think I've been talking already.
No, we are still at least 12 minutes.
Oh, okay. Well, I wanted to jump ahead too much, so I might show you some of the earlier things. Okay. See, this is what really the astrochemists do. They put together a series of chemical reactions, and they say, okay, the molecule M or the molecule Y are formed this way, and then the molecule M is destroyed in this way. You create a network of chemical reactions. And then you write down, well, I'm sorry I had to write down equations, but this kinetics equation simply means that you want to follow the evolution of these molecules in time. And the cosmologists tell you what happens to the redshift, which is this equation connected with the Hubble constant, and what happened to the photons, to the photon bath of a star, which is actually illuminating this exploding matter. All of this goes into a series of equations, and they involve, this is a simple case, it's the 4 atoms that I mentioned to you at the beginning, and look at how many reactions. It's a good thing that you can't read them, because this transparency is only meant to show you how complicated the system is to look at the molecules containing lithium when you can only have hydrogen, helium, and lithium. So you've got 3 atoms, and yet you have a network of reactions, all of which have to be studied on Earth in order to understand how they may behave in the universe. So you solve a series of equations, it doesn't matter what they are called, and in the end, what you get are abundances. So this is what the astrochemists do. They observe the early universe, the redshift of the early universe is of the order of 1,000. And then you look at the abundances, these are a log scale of the various molecules. Notice that this tells us that there's a redshift already of 10, so a redshift of 10 is about 1,000 years. Then you have hydrogen, which is present within a fractional abundance with respect to the atoms of 10 to the minus 5. So that means that the astronomers have to observe the faint signal of the H2 molecule, which is 10 to the minus 5 less present than the hydrogen atom. So this quantity is crucial. This whole network result is telling the astronomers when are we going to observe this. And in fact, H2 has been observed, but at a redshift in this region. All this redshift from the early universe has never been observed. So this is another point. The model of the molecules in the early universe are indispensable for creating the conditions of the universe that we know now. But we have no signal that comes so far back from the early universe for the molecules. The oldest molecule, the oldest signal that we have observed is of the order of 10, redshift 10 for the H2 molecule. So there is a conundrum there. We know that the molecules existed and they have been essential for cooling the early universe, but we have no signal coming from those molecules to us. Now, why is that? Because if you look at some of these examples, you see that the abundances, for instance, this is a molecule that must have existed because it's a polar molecule and would be very crucial for the cooling of the early universe. But the abundance is of the order of 10 to the minus 10. The signal would be very faint. The astrophysicists put a threshold to how faint is a signal before you see it. And it's of the order of 10 to the minus 15. But 10 to the minus 15 means that you can observe things at a redshift of only 1,000. So you're far away from the early universe conditions. And goes on for various molecules. This is another important molecule, but the abundance is 10 to the minus 15. So this molecule could be observed. And this is in fact, and the same happens to the molecules related to lithium. So lithium atoms has been observed, lithium ion has been observed, but the molecules are down here. Abundances of 10 to the minus 18, they estimate. So means they have never been observed. So we really need to improve on the quality of the machinery that we sent up to observe these objects in order to possibly see signals from these molecules. So let's say that the message, I might as well get to the message more quickly, having bored you for too long, that we need better observational instruments. A lot of involvement of collaborative efforts now are going on creating better radio telescopes, satellite telescopes, and interstellar probes in order to improve our possibility of observing much fainter signals. We have to go down something like 5 orders of magnitude. If this will occur, then we'll be able to observe these early species, because all we know about the network of the chemical development requires the presence of these molecules. So what happened after that, after the early universe? Then bigger atoms were formed, and all these atoms and the ions, by radiative association, formed the carbon-rich molecules that we know. And the density of this baryon has increased in all the atmosphere of the planet because of these collisional reactions. So this is another world in which chemistry plays an important role, and this role is the one that produced the larger number of molecules that we know today. So in essence, the early universe worked with only 3 or 4 different molecules, but they were networked in such a complicated way that probably our way to look at it is very likely they were essential to the cooling in the first million years after the Big Bang. So that cooling had to have, before the separation of photons and baryons, you needed to have the molecules. But the molecules had to be seen, and this hasn't happened yet. So now we know that there are more than 300 different molecules of various sizes, and the variety and diversity is indicating that the molecular basis of life began to exist in our planet, and who knows, it might exist in other planets. But of course you have to remember, and this is a warning to everybody, that comes from a famous cosmologist, which is Stephen Hawking, who say that cosmologists are known to be often in error, but they are never in doubt. So although we have never seen these early molecules, we are convinced that they existed and they were essential to the development of chemistry. And thank you very much.
Thank you very much for this beautiful talk, and we have time for some questions.
Yes, yes. The question is that if you look at the... That's right. If you look at the red shift, this is one of the problems. You're now falling very rapidly into the region of radio waves. So you really have to select signals that now fall into the region of the radio waves, and you have to, and it's very hard to have detectors that can be able to detect those signals. That's one of the reasons why you don't go back to the large Z. The large red shifts will move you every one value of Z moves the wavelength of about 1 order of magnitude. So you move from the UV or the infrared down to the radio waves, and this is the real problem.
Other questions? I have a curiosity, meanwhile, that is, I suppose that from knowing, from the probability of collision probability, you can get the density information of the early universe. The information now was the density of the early universe.
Yes.
This is, I imagine, compatible with other system of determining the density at this stage of the universe.
Yes. Well, of course, collision frequencies are so low that it's very hard to estimate their presence. So the way this is done is through photon densities. So really, whenever you see that this emission is there, but of course there is also the problem, and in between the stars, in the interstellar medium, you have a lot of dark clouds, regions where all this debris is screening the outer stars. And this is very good, because if you're screening the stars, the temperature inside the screen region goes down. So we think that most of the universal chemistry takes place in these dark molecular clouds, regions where light doesn't come out very easily. So the chemistry takes place there. How do we know this? Well, again, as I showed you here, a cosmologist is never in doubt. So we think that the actual factors of chemistry are the dark clouds. But these dark clouds emit very little light and very faint signals. But once you're patient enough and you look at those signals, you discover that a lot of molecular signals come from these dark clouds. So there are regions of the universe where the density is higher because of this tail of the debris from the explosion of a star. So the stars are continuously formed, and they all seem to be formed the same way. Sorry, am I talking too softly? So the stars are continuously formed by explosions. So you are continuously having this cooler debris coming closer to a particular burning star. So depending on the size of the stars and the debris, you create a planetary system. The one that I showed you, oh, well, it's a long way back, in which you actually see, let's see if I get that. Yeah. See, this is, you're actually having a hot object, nuclear reaction object, rather large, that has been produced by an explosion, and the smaller parts are moving away from it, but are kept within its influence by gravitational pools. So we have a very hot source, we have cooler fragment, and there is a denser region here. And this is the region that the chemistry could take place. This eventually will develop over a billion of years, will develop in accretion. So some of these little parts will get together, as you see here. And then finally, you'll create a sort of star with a radial distribution of planets at different distances. So ours, and so all of this is controlled by relative masses, gravitational pools, original explosion, which create the kinematic initial conditions, and then the cooling of the system. The chemical cooling occurs down here. Anyway, this is all very pictorial. Was that clear, or did you?
Well, I have a complete ignorance, so somehow I got lost somewhere.
Oh, I'm sorry. You're not the only one. You're not the only one.
I think I understood the cooling down.
Okay, very good. So that's one.
I understood that temperature is a matter of wavelength.
Yes.
What I didn't grasp is the reverse process. It's the warming up, because sometimes the warming up happens.
Well, no, I didn't quite get this. You have this original Big Bang. So they're moving away, and this is kinematics. They are fast, but they are big, whatever they are, and therefore they pull each other. And if the pulling, which is the gravitational pull, prevails, they collapse again, and they will explode again, forming a different type of structure. So once you explode, there are areas in which these nuclear reactions, the ones that goes on in the stars here, burning helium, keeps going. So the star not only produces light, but it's also a massive object. So we are kept close to the sun because its mass is pulling us in. And if it were slightly bigger and too far away, we will be all dead. If we get closer because we are smaller, we will also be dead. So it's a balance, the temperature of these little fragments here. It's a balance between attraction and kinematic explosion. And what we know is that during this explosion, if you have fragments which are cooler, something has to get rid of the energy. Good. Sorry, am I transforming this in a sort of
I think we can continue during the coffee break.
I think we all need coffee now.
I would like to thank both the speakers. Hot coffee. So let's thank both the speakers.
everything is fine. People ask me to give it in German, and other people ask me to give it in English, so I give it 50-50. Good. Please speak slowly. Yeah. Io lo farò dopo, perché se non vedevo tedesca, lui diceva che a casa arrivo, deve essere una lista. Sì. bleiben Sie hier, einfach hier stehen bleiben. Weil er ist ja immer da rumgelaufen und hat alle immer umgeschaltet.
Ja.
Prima.
Ok, benvenuti a tutti, herzlich willkommen und welcome to this session which continues the preceding one, and we will have two more presentations. The first one by Professor Horst Stücker, and he has been requested to give his talk in English by some people and German by other people, so he told me that he will give his presentation in part in German and in part in Italian. One recommendation then for the discussion, everyone who wants to present questions will receive the mobile phone, because it is necessary to speak into the microphone in order to have the streaming transmitted abroad, broadcasted. Thank you very much. So, Professor Stoker, you are welcome to talk on discovery potential at the European Science Facilities Fair and CERN.
Herzlichen Dank. Ich bin sehr glücklich, dass ich eingeladen bin. Auch Herrn Hesse danke ich, dass er dieses Programm im Prinzip weltweit, glaube ich, sogar unterstützt. Bin sehr froh, dass ich zum ersten Mal südlich von Rom bin. Also ich war schon in Sizilien, aber das zählt ja nicht als Italien. Ich freue mich sehr, Sie alle kennenzulernen. Es sind nur sehr wenige Kollegen, Giacomo, Peter Reiter, die ich von meinem Fachgebiet her kenne. Aber Sie werden sehen, Professor Gianturi hat einen perfekten Einführungsvortrag gehalten, sodass ich eigentlich kaum noch Zeit brauche, um ein paar weiterführende Bemerkungen zu machen. Ladies and gentlemen, dear colleagues and friends, the facility this is very loud, maybe I should take this off. Die Untersuchung, die wir machen, no? But this is it's very loud. So maybe like this? Okay. Okay. The physics and chemistry, technological advances, and other things which we plan to do with this facility fair. That's the wrong way around. But I only have here things like on this side. That the facility fair is offering is very interesting indeed. We go, I hope I went in the right direction. Yes. So, the facility fair, which is shown here, is a roughly €1.5 billion facility, which is presently being constructed right next to the lab, which I had the pleasure to represent for 8 years now. This is GSI, a national lab of the Helmholtz Society in Germany, funded 90% by the federal government of Germany. The fair facility here is a collaboration of 51 countries. Similar to CERN, I would say, although considerably
smaller. We have an annual budget of €250 million. CERN has an annual budget which is 4 times bigger. Also, the rings they have are 5 times bigger than our rings. We have about 8 rings in total planned for the fair facility, if I can call this a ring. And we have lots of experimental stations. Other than CERN, we are not focusing on proton-proton collisions, but this fair is a facility for anti-proton ion research. Ions we have heard just in the last talk, and all I can say, he's a slim gentleman. I'm responsible for heavy ions. Heavy ions means not lithium or helium, but uranium and gold and silver, all the good stuff. And of course, it's, as he has shown already, much, much less abundant in the universe. And all the heavy ions, heavy nuclei, come in very many different species. They are called isotopes. They have the same electric charge, so they have the same number of electrons around them when they are an atom, but, that's the big difference, they have different neutron numbers. You know, hydrogen comes as a simple proton with an electron around it, but you can add a neutron to the proton. The chemistry is not much affected, but the nuclear physics is completely different. And this is what we are going to explore with very many different heavy nuclei. The countries which own this fair facility are shown down here, and there are quite a few Mediterranean countries here, Sweden, for instance. No, that was a joke. Spain, Slovenia, we have a Black Sea country here, Italy, India is, of course, not Mediterranean. France is Mediterranean, and Austria was Mediterranean, but that's long ago. Okay. There is, however, 51 countries involved, and I will show you in a minute a map where you see that it's actually a worldwide facility. About 30% of FAIR are owned by countries which are outside of Germany. Biggest owner here besides Germany is Russia, and the second biggest is India. India put €50 million capital into this facility. Let me just find out how, yeah. So what my task was, as a director of GSI, which is a Helmholtz Center for Heavy Ion Research, to make possible the transformation of our national lab as a base for the international facility for anti-proton, anti-matter, one can also say, and ion research. This is the FAIR facility. So here I show you the national, which is shown here, and the international collaborations. Wir haben in vielen Ländern, wie Sie sehen können, Kollaborationen. In Brasilien, Chile, Südafrika. Wir haben in Israel, in Palästina und in der Türkei, aber auch Australien, Japan, China, viele Kollaborateure, viele Nordamerikaner, auch Kubaner und Mexikaner. Natürlich viele Institutionen in Mitteleuropa, Südeuropa, and this we discussed already. Zurzeit, at present, we have roughly 1,200 external users. At GSI, we will have about 3,000 international users when FAIR becomes operational in about 6 years. Wir haben 170 Forschungsinstitutionen. Inzwischen sind wir nicht mehr 35, sondern 51 verschiedene Staaten. Was ist Schwerionenforschung? Es ist Theorie, das hatten wir eben gesehen im vorherigen Vortrag. Es ist Experiment, es ist aber auch computerbasierte Simulationen, die Lösung der Gleichungsnetzwerke, die gerade von Gianturi gezeigt worden sind, brauchen Computing. So GSI, this is the national lab, which is, let's say, the mother lab originally, but it will cease to exist as soon as we have formally fused the two laboratories. It was founded 45 years ago, and as I said, mostly funded by Germany as a whole, and the state of Hesse, the state of Rheinland-Palatinum, Mainz and Thüringen. Diese Staaten der Bundesrepublik, die bezahlen das Budget der GSI. Die Mission ist ganz einfach: Bauen und Betrieb von Beschleunigern, Realisierung und Start der FAIR Facility. Und wir haben ausgezeichneten, sage ich sehr gerne, Schwerionenforschung, Aktivitäten hier laufen, in den nächsten 5 Jahren auch noch. Wir haben 1200 Mitarbeiter und wir haben, jetzt sind es 1500, aber wir werden insgesamt 3000 Mitarbeiter bei FAIR haben. Mitarbeiter ist das falsche Wort. The word should be scientific collaborators all over the world. They don't have to be technically employed by GSI or by FAIR. So Helmholtz, what is Helmholtz? Many people know Max Planck. Many people know Fraunhofer. Max Planck is a small institute on our scale, 100 people or so. We have the large research centers of Germany combined to form a club. The club consists of these 16 independent and separate centers. We have about 40,000 employees, half of which are scientists and engineers, 6,000–7,000 doctoral students, and roughly €4 billion budget. So it's a little bit like the Department of Energy in the United States, combined with the National Institute of Health in the United States. But the budget, of course, is much, much lower than in the United States. We don't do military research. We have 6 research fields. GSI is located here. The Helmholtz-Gemeinschaft sits officially in Bonn, but most of the action after reunification of Germany has now moved to Berlin, but our ministry still has a predominant seat in Bonn. There is cancer research done here in Heidelberg, DKFZ. There is DAISY, which is electrons, the very light guys. We don't even want to talk about them. We are the heavy guys. And there is liver and pancreas research done here. There is infection disease research done here. Rossendorf was a former DDR, GDR institute, is now a member of Helmholtz. Jülich and so on. So these are the programs which we have in Helmholtz. This is the national, as I said, part. But Helmholtz' first international institute will be the big I in FAIR. FAIR, I think, will also in the future be funded to 50% or so out of a Helmholtz band, which is matter here and health. Helmholtz also has energy production, energy savings, earth and environment, key technologies, computing and solid-state physics, and the German equivalent of ESA, which is the DLR in Köln. So what is GSI? It was founded, as I said before, about 45 years ago. It is, from the function, it's a national lab, but it has predominantly international users, and 35% of our workforce are non-German citizens or non-German origin. The future is our international facility. We have a strong strategic connection to universities all over the world. But within the state of Hesse, we have special funding of the state for Marburg, Gießen, Goethe University in Frankfurt, Technical University in Darmstadt, and Heidelberg and Mainz also receive special funding. This is how the present situation looks like, and if you watch it now, wenn Sie jetzt aufpassen, dann sehen Sie, die neue Maschine wird sehr ähnlich sein vom Konzept wie die jetzige Maschine an der GSI. Es ist hier hinten eine Ionenquelle. Sie sehen immer den englischen Text. You can read the English text here. Eine Ionenquelle, die produziert leichte Ionen Die werden durch einen Linearbeschleuniger immer geradeaus auf 20% der Lichtgeschwindigkeit gebracht, 20% of the speed of light. Dann ist schwierig. Ja. Okay, sorry. Yeah. From 20% of the speed of light, we go into a so-called synchrotron, which many times runs the particles in circles here and spits out 90% of the speed of light particles, which then go into the detector areas, into the storage ring. We just built a new storage ring here, and into the analysis section of all these detectors. So the basic idea technically is this is a problem, it's too loud, no? Okay. Okay. Yeah, I understand. I understand. Okay, have to find a compromise. So the idea is the GSI is, so to say, the driver machine which gives the beam to all the experimentalists which come from all over the world. And this driver machine here of GSI and the experimental stations is now for a fair increase by a factor of 5. So the new area is roughly here, and it's 5 times bigger in space and 2.5 times bigger in budget than the GSI. And what we do is storage ring physics with bare atoms, with exotic nuclei, and fragment separation here. And if you have any questions, my colleague here is involved in this science and in this physics. He can give you the answers in Italian, which I can definitely not. So the research goes from fundamental research in the structure of matter to applications and transfer of technologies, and this is of course something all governments want you to do nowadays, applications and transfer of technologies. And I will show you a few examples which relate to the previous talk and which relate also to the discussion which we will have. So what, for instance, did GSI accomplish? Just for a general idea, this is the famous system of elements as it existed about 20 years ago. You have here the hydrogen, the helium, and the lithium. Those are the only chemical elements which are produced, we just heard it in the talk, during the time, let's say, the first 3 minutes after the Big Bang. All the other elements don't exist early in time. They just simply do not exist. There's no physical process known even which could allow us to produce this huge wealth from carbon to, here's a polonium or lead. It's not possible to produce them in the Big Bang. Impossible. So where do all these other nuclei come from? And this is a question which is particularly pushed by the FAIR facility, that one wants to explain where these elements come from. Well, you say, well, I heard that this is cooked in the sun. Not true, and we will come to that in a second. It's very complicated. Anyhow, at GSI, we have been able to extend the periodic system of elements by these orange guys here, from borium through hassium. Hassium is actually for Hesse, especially for you. Then we have the meitnerium for Lise Meitner, Darmstadtium, well, this is the city where GSI is located, Röntgenium for the big, I think, one of the first Nobel Prize winners, or if not, even the first Nobel Prize winner in physics, and Copernicus, which gave the name to element 112. I personally like the 111 even more for other reasons. We have now also produced, together with lots of colleagues from all over the world, these elements here. They have first been discovered in Japan and in Dubna in Russia. So there is competition, stiff competition. Here we were first, here they were first, but we have confirmed 13, 14, 15, 16. We think we also have confirmed 17. We have not been able yet to confirm 18. We tried to do 2 new elements, 119, 120, until now we have, I would say, a faint thing. I don't say a signal, I say a thing which looks like one event of 120, but there is lots of information missing, so we do not claim discovery yet. Only the laboratory, only the collaboration which can clearly prove the existence of a particular element is allowed to name it. So that's why we gave preferably names of scientists from Germany here, C.C. Borgium, Americans, Dubnium, that was of course a Russian group, and so on and so forth. So here you see the naming of our heaviest element which we discovered. Now we have made also heavier elements, and they are discovered by chain of emitting helium nuclei, alpha particles, from this created single nucleus. We really create one single atom, one atom, which decays in a chain of 5, 6 helium nuclei which are spit out. The system does that to release electric energy. You kick out 2 protons plus 2 neutrons, and the 2 protons carry away energy, much energy from the very highly charged nucleus, less and less energy the lower the charge becomes. So it's actually a very clean signal if it is all in one position. I just told you that we believe we saw element 120, but we only saw the first 1, 2, 3 alpha particles. We didn't see the rest, so we don't know what happened. Possibly a fission happened or something, we don't know. The other application, second example, is cancer therapy. In Legnaro, CNRO, Knau, and other places in Italy, this is done also. We have developed at GSI this technique of electrical monitoring the beam so that you can actually go into the brain of patients which have an ugly tumor here, and no more scalpels. It's as precise as a scalpel, and it's extremely efficient in fighting tumor cells. We have healing rates here for the primary tumor which are 85 to 90%, and we have 0 side effects, 0. So you have to imagine it like a dead person walks into the room, has probably like 3 weeks to live, 4 weeks to live, sits down, the beam comes in, stands up and takes his bicycle and drives home. This is really a tremendous effect. The whole treatment takes about 2 minutes. You come back 10 times or so. And this is in particular very effective for brain tumors, but also prostate tumors, bone tumors are used. The reason is a strange effect, a physics effect, which you see here, the so-called Bragg peak. If you take X-rays to treat a tumor, as a function of the penetration into the body, be it breast or here, the X-rays produce a lot of energy in the living tissue in the first few centimeters, and then they keep on producing damages. Here is the damage done over the whole distance while they go through the body. The ions, they slip through the flesh and dump all their energy in one point, which is only a millimeter in height, in length and in depth. Also diese Methode, Krebstherapie mit Ionenstrahlen zu machen, ist jetzt auch in Kliniken schon am Laufen. Ich glaube, Knau läuft noch nicht mit Ionen, aber mit Protonen. Das CERN macht so etwas auch. Und unsere Klinik hier, das war die Pilotphase in der GSI, das ist Professor Debus. Wir haben 500 Patienten behandelt, eine tolle Tumorkontrollrate, keine Side-Effects, und unsere Krankenversicherungen bezahlen das, auch die holländische Krankenversicherung und die österreichische Krankenversicherung. Wir haben jetzt eine große Maschine gebaut, die ist seit 3 Jahren, in 3 Jahren läuft sie richtig voll Flash. Wir haben jetzt mehrere tausend Patienten schon behandelt, sehr erfolgreich. Am Uniklinikum in Heidelberg steht die Maschine. Wurde von uns gebaut, aber betrieben wird sie von Heidelberg. Wir haben auch eine neue Maschine, die läuft jetzt im Herbst an, in Marburg, am Uniklinikum Marburg-Gießen. Eine Maschine in Shanghai, und es werden von anderen Staaten auch Vorschläge gemacht, unsere Patente und unser Know-how da zu benutzen. Und wir machen, wie gesagt, enge Kollaboration mit dem Centro Nazionale Atroterapia in Pavia, Onkologica. Aber ich bin nicht sicher, ob die schon Patientenbetrieb haben. Weißt du auch nicht. Also wenn, dann jetzt, ja, ganz nah bevorsteht. Okay. So, jetzt gehen wir über von der GSI, das war, was hat die GSI gemacht, historisch, die letzten 10, 20 Jahre, zu dem neuen Beschleuniger. The new accelerator, you have seen, this is the GSI. The new one, I told you, is 5 times bigger, 5-mal größer. This is the present synchrotron, this is the new one. This all, the forest here has already been chipped down, 24 hectares, 24 Hektar Wald sind weg. Die hessischen Grünen haben nicht protestiert, no protests, because Darmstadt calls itself a science city. No protest, nothing in the news, but everything is going fine. We have put in 1,500 big piles, 1.50 meter diameter of 60 meter depth, because this is basically swamp area. So we have a little Venice here. And this was finished last year. Now we should have started digging the big tunnel, but the usual problem came up. Changes over the period which we prepared this, changes in fire safety, in radiation protection, which follows from the fire safety, now make necessary that we rework the plans in detail. So this will be probably a delay of 2-3 years. And of course, all the international partners are very concerned how the German superpower in technology and engineering cannot even manage to dig a simple hole of 20 meters deep and 5 kilometers long. It's not the digging which is the problem, it's the getting the whole process accomplished by the bureaucrats. That's life. So the long-term perspective for GSI is this fair project. The interesting part is we will have gigantic increase in beam intensities. We already now are the world champions in beam intensity. Die Strahlintensität, Beam Intensity, die Strahlintensität ist jetzt schon Weltrekord bei GSI. We are the world champion in intensity. Very fine beam. But in the fair facility we'll have 1,000 times better beams. The beam energy, how fast the guys are, will also be up, but that's for us not so important. That would be important at CERN. For us it's more important to get the intensity up, so-called intensity frontier. We can do very rare processes with very heavy ions. Nobody else in the world can do this with speed of light. There are other labs which can do that, for instance his lab, but the speed is smaller. It's 10-20% of the speed of light, and we go to 99% of the speed of light. So we will also be able to make antimatter and antimatter beams, and a very good beam quality. And I always sell this as saying this is one machine which serves 4 communities. So you get 1 for the price of 4, no, 4 for the price of 1. And this is a big issue. So we'll construct this in modularized version. This is the price for the machine in 2,005 euros, and it's in 4 different fields: atomic physics and plasma physics, plus applications. Then I would say producing the interior of neutron stars, this is what is done in this experiment, very high densities of protons and neutrons and so-called hyperons. Like they only exist in neutron stars in the universe. The whole physics here and science is described by the header cosmic matter in the laboratory. And we go over all the timescales which the previous speaker has presented. We do very early universe, antimatter matter, and antimatter-matter disintegration, which particles were there in the very first moments of the universe, microseconds, not only seconds, microseconds, millions of a second. Then we go from there to forming of atoms, which happens in the first few minutes, but only these very light atoms. We can study atomic physics for these light and also for very heavy nuclei. Then the formation of nuclear structure and nuclear astrophysics in star explosions, supernova explosions, and neutron-star mergers and encounters. So this basically is a time machine, a time warper. You can go back in time 14 billion years, 1 billion year, 100 million years, and now. And we will start to investigate something which has never been observed, but it must be there, according to the best theory we know which works, is gauge theory, so-called quantum chromodynamics, namely glue balls, but nobody has ever seen them. It's an elementary particle which does not contain any quarks, but it's as massive as 2 protons. But nobody has ever seen it, but it must be there, because field theory calculations prove on the computer they are there. So why have we not observed them? And that's what we want to study. Difficult is, of course, to build this accelerator. So we worked very close together with Pasquale in Fabricatore in Genua on fast cycling superconducting magnets, which is very successful, was tested in Milano and Torino, but came really, the original work came really predominantly from Genua. Then we have loaded cavities for, of course, our super fragment separator, which is very interesting for 1,000 people worldwide. Extremely high vacuum. The high vacuum here is actually better than in the interstellar gas and clouds, which we discussed in the previous talk. 10 to the minus 13 millibar, 10 to the minus 16 atmospheric pressure. 16 order of magnitude smaller than the air which we have around us. And very important for us is also cooling the beams. If you don't cool the beams, it is not existing for a long time. So only if you cool the beam, you can have a steady beam for hours and days and years. So what is our experiments? There is the antiproton physics experiment called PANDA, which produces very rare particles which must have existed in the Big Bang. I just noted. Then we have this neutron star detector, which can look into the interior of neutron stars without having a neutron star here, but producing a little bit of neutron star matter actually here in the laboratory. Then this is the nu star detector, which is a huge spectrometer which has 3 different outlets for nuclear astrophysics and atomic physics, plasma physics. Plasma physics here is shown for making energy production feasible in inertial confinement fusion processes, materials research, biophysical research. There's Marco Durante is the head of this division here, biophysical research. We are an ESA, European Space Lab resource as GSI, and future also for FAIR. So what is the antiproton machine idea? Here is the mass of the particles given in terms of the proton mass. This is the proton mass. This would be the mass of deuterium. This is the mass of an alpha particle, helium-4 nucleus. And lithium, the lightest lithium, is this guy here. But now we claim we can do these new states, glue balls, extremely interesting. As I said, nobody understands why they haven't been observed, but it's difficult to measure. But they must be there, they must have been produced already, but nobody has seen a signal. We believe we can do this very nicely. This is a guy, as you see here, which consists of nothing. Of nothing means no real particle involved, only fields. So it's like a very hot system which consists of fire only. Wie ein Kugelblitz, würde man in Deutsch sagen. So there's no material particles, no spin and 1/2 particles, no protons, no neutrons, no quarks, no electrons, only fields. What I actually do every morning when I step on the scale, my wife complains, again 100 kilo. I said, no, it's not 100 kilo. It's only 1 kilo. 99 kilo is pure quantum foam. Don't worry. So this we want to look for in the future. And we can go actually all the way up to almost the lithium mass, 5.5 times the proton mass. So we can look for very heavy guys, which are called charmed glue balls, but also so-called oddballs, crazy stuff, which according to quantum chromodynamics must be there. I'm just writing a paper where we believe that at CERN, at the Large Hadron Collider, we should also produce these guys. And we believe we have signals to prove that the guys are there without even having to see them. That's a funny new idea. So here I show again the oddballs, which have the wrong spin and the wrong statistics. Then the second experiment is the compressed baryon matter detector. I told you this is there to look into very high so-called baryochemical potential. So it's a chemical potential for baryons. Those are protons, neutrons, and heavier particles. And temperatures which are gigantic. The temperature of the surface of the sun is, let's say, 5,000 degrees. The temperature in the middle of the sun is 15 million degrees. And these temperatures here are gigantically much, much bigger than those. And we believe that at CERN we can make temperatures which are shown here, and at FAIR we will be able to make temperatures here. At CERN we have basically no density of baryons. We will have very high density of baryons, up to 10 times the density of normal nuclei. And this is actually densities as they should be observable in the interior of neutron stars, but we never can go there. We have to produce them on Earth. This is the detector, and you see here this little person, so it's a big detector, and lots of groups from all over the world are involved in this. Here you see calculations, simulations. This is the density, this is neutron star density, and we believe different calculations that for a rather reasonable amount of time we can produce little pieces of neutron star material. Technically this is very difficult. I don't want to go into technology issues here. Then is our flagship at GSI, which will also be a flagship of the FAIR project, namely the original question which we heard in the previous talk: how have we been able, or how has God been able, how has nature been able to make nuclei and atoms? And we heard in the previous talk that in the Big Bang only these nuclei down here have been produced. Nothing out of this. There's 3,000 nuclei up here, but he showed only 3, let's say 4 different nuclei. If you include isotopes, maybe 5 or 6 nuclei. But they're all sitting down here. 2 protons, 2 neutrons, that's a helium nucleus. That's all which can be produced in the Big Bang. Where does all the other stuff come from? Diese Frage ist eine alte goethische Frage, was die Welt im Inneren zusammenhält. Diese Frage hat man versucht zu beantworten und hat es vielleicht auch geschafft, ungefähr in diesem Massenbereich, nämlich durch Kochen von diesen leichten Atomkernen oder Ionen, die im Urknall, dem Big Bang, dem Urknall hergestellt wurden, bis zum Eisen. Das sind die Kerne hier so bis zur Masse 50. Wo haben wir Eisen? Hier irgendwo. Nee, 28 hier. Masse 50 ist ungefähr hier. Alle anderen Atome, alle anderen chemischen Elemente können nicht hergestellt worden sein. Unmöglich, die zu produzieren. Absolut ausgeschlossen. Jetzt habe ich 3 verschiedene deutsche Terme benutzt, einer muss hängen bleiben. It's not possible to produce heavier atoms, heavier nuclei than iron for a very simple reason. These guys here, they are the most deeply bound elements which are possible to produce by a process which you would call exothermal. So you create energy by producing these nuclei. These here, if you would want to go from here to there, you would need to put energy in. But this energy is not available in normal suns, stars, in the universe. This energy is not available. So we have no idea where these nuclei all come from. These are stable nuclei. There are thousands of other nuclei around. Part of them have already been observed, actually several hundred, for instance, at GSI. But we have no idea how the universe made them. Absolutely no idea. There are some crazy guys, the Giacomo, for instance, they claim it could have been that in an explosion of a very big star, you can create very few of those. Then these guys are emitted. The universe collects them again, cooks them again, and 100 times explosion, supernova explosion it's called, of a very heavy star has to occur until you even come close, not perfectly fit, come close to the observed abundance of these nuclei. Some people say that's not the right process. It's the so-called right process, R process, actually rapid process in an explosion. What happens, the system does not walk along this line. The system goes down here and produces completely unstable stuff, which slowly gets up to here and maybe even higher, has to go all the way to uranium. And then, when this explosion stops, the whole system decays over to the line of stability here. Very strange process. Other people say this is nonsense. There is an R process, the right process, the rapid process, but it is in collisions of neutron stars. Two neutron stars collide, swallow each other, vanish, for instance, in a black hole. But again, some material is kicked out, flies through the space. We want to observe it. It decays and it produces these guys. Again, you need many times the process to be repeated in order to get to the abundances. Let's see whether any of these processes will be confirmed, but this is basically the FAIR project to find out what are the properties of these nuclei here, which are unstable. They have never been produced before. Try to find their lifetime, their binding energy, and check out whether they really go there. This is the NuSTAR collaboration, almost 1,000 members worldwide, many Italians on there. Then there are even more crazy people who say, well, you don't only have the new dimensions in the chart of nuclei, which are protons and neutrons, but you can also have so-called strange particles, particles which only live when they are bound. The neutron is, for instance, also unstable. The neutron only exists for a long time when it's bound in a nucleus. A normal neutron decays after 888 seconds, which is 10 minutes. I don't care. So this is the idea, to go into a new dimension where there is so-called hyperons, strange particles added. So you go into a new dimension up from this proton-neutron plane and make hypernuclei. And this has been already studied for light nuclei. There are a few known, but with the FAIR facility, we will be able to do anti-nuclei and hypernuclei, which carry many so-called strange quarks. This will be interesting, has not been observed yet, only these very light ones. Here is the lithium and the helium and hydrogen. So basically what we would claim is that these nuclei, which were discussed in the previous talk, were there, but there should also have been some there of hyperons, but they unfortunately are light and decay again. So this is the beam parameters, which shows you will have tremendous beam intensities, which come actually from the injector GSI into the big rings. And the energies here are given in masses of the proton mass. So this says we have 40 times the mass of the proton as its kinetic energy. So very relativistic case, and only therefore we can make antimatter and so-called hyperon matter or hypermatter clusters. This is the spectrometer. As I said before, lots of Italian scientists are engaged in this, but it's actually a worldwide collaboration from India to Brazil, from the US to South Africa. Thank you.
Thank you very much. And then we have time for a couple of questions. Yes. Please use this one. And this may be. The possibility of using FAIR for ion therapy is really very, very interesting. But I seem to remember that there is a similar machine already active in Heidelberg, or am I mistaken?
I showed that. We built this machine in Heidelberg. We pulled out of the treatment at GSI because this is too big a machine. For the Heidelberg machine is only 100 meters long and not 5 kilometers. But for the future, for FAIR, we have a new patent, Marco Durante and myself, which is different from the old idea with the Bragg peak, where the beam stops in the tumor. We now have, you may call it, diagnosis and therapy at the same time, namely very high energy, that's why we would need FAIR, very high energy protons, which go through the tumor. But on the other side, you focus the beam again, so you get an image of the tumor. The contrast is good enough. We have done test experiments in Los Alamos and in Brodwina in the USSR, the former USSR. And this can then do both, show where the tumor is and kill him. We cannot do this with the present heavy ion beams. There we need to have a normal positron emission tomography to find where the beam is, and a separate analysis with X-rays to find where the tumor is. But with high energy protons you can do all in one step, and with much higher precision, so you could even go for small metastars. We could go to millimeter precision in the present setup, and then in micrometer precision with high energy beams.
How many positions would you have here around the ring? How many bedding for patients at the same time?
This has only the concept proven. So not even a patient treatment has happened. So we'll have to wait to answer this. But in Heidelberg and in Marburg and in Shanghai, it's for the Bragg peak machines, it's 1,000 patients per year. 1,000. We believe, we have estimated in Middle Europe, there is a commercial interest from hospitals for about 10,000 people per year. With our new idea, this will have to wait. This will be 10 years from now before we can even test it on patients. This is always a very long process before you get the okay to use a medical application with beams.
Any more question? One more? Yes, please.
In this, what you have commented just now, this other possibility. Do you produce secondary particles with the energy protons on the cells?
No, the proton directly.
Yeah, I see.
10 GeV proton.
Yeah, 10
it
GeV.
gives a very nice resolution.
And
the secondary particles, of course, are there, and one has to check out. They will produce pions, but the pions will go out before they can go into muons. You will produce neutrons, you will do nuclear fragmentation. But this is all what we call gray particles. So the ionization is not so bad. So I think it's less demanding than the Bragg peak method.
I see. And the other question is, when do you think that FAIR will be able to answer this question you were just showing?
Well, this is not so difficult a beamline. Maybe I can show it on here. So this is the primary beam in the little synchrotron, then it goes in the big synchrotron, and then we have total of 4 target stations. One is for CBM, very brief beamline, very simple from a machine point of view, very simple setup. The other one, what you would like to have most, is of course already complicated. This is a 200 meter long spectrometer and 200 meter long superconducting spectrometer. 200 meter long superconducting spectrometer with a lot of different ways of doing it with lots of different magnets, complicated. The antiprotons are even worse. New proton linac, this production target, first Cooler ring, second Cooler ring, high energy storage ring, and a 700-ton detector. This is all complicated. This one is easy, fixed target, and this is the hall for the medical stuff. Very easy, it's a fixed target beamline. no big deal. And the detector we have already now, as I told you, used it somewhere else, but it's now at GSI, the Pantera detector. It's based on very fast optical chips which read out, that's too difficult now to explain, but this already, the detector already works, so we just need the high energy protons, that's all. So that could be done in, let's say, 2021. Thank you.
Any more questions? So, thank you very much. And it is now time to call Professor Pierandrea Mandò from Florence, who will speak sulle attività dell'Istituto Nazionale di Fisica Nucleare nel campo delle analisi sui beni culturali e del monitoraggio ambientale in una prospettiva di collaborazioni europee. He will give his talk in English, and so it is on applied physics to cultural heritage study and preservation, and within a frame of collaboration within Europe.
Okay, so first start with the Larsen. First of all, thank you very much to Alessandra and Loris who invited me to give this talk. I am unable to give a talk in German. I would be able to give it in Italian. I was thinking it might be just to change to give it in French, but I think that English is better for everybody. Actually, first of all, I start, let's see whether this works. Yes, it works. Just to tell you what the INFN is, the Istituto Nazionale di Fisica Nucleare, which is a national institution of research working basically in the field of nuclear physics and is, as you see, distributed on the territory with 4 national laboratories and 20 sections, what we call sections, units. It has, it's not the right place where to stay. Yeah, no, I know, but well, maybe here it's better. Basically, the purpose, the mission of the INFN is doing nuclear physics, and therefore I go on. Okay, so promoting, coordinating, performing scientific research, nuclear, subnuclear, astrophysical, astroparticle physics, physics of the fundamental interactions, but also already from the statute, you see that we are engaged in favoring innovation, promoting the transfer to society of the acquired knowledge and technologies. And among those, maybe the most, the best known are those just to medicine. You know, there are a lot of nuclear physics applications to medicine. Some of them have been just mentioned by Professor Stöcker, and indeed also in Italy, INFN has been in the National Laboratory of South in Catania, the first Italian place were doing hadron therapy with protons, and more recently in Pavia, INFN has been one of the main actors of the construction of the protosynchrotron. Not protosynchrotron, actually, it's a synchrotron because it will work also with carbon ions, which have more specific features, in some cases favoring the selective cure of the tumors. But I won't speak about these. I will speak about these things if I have time, all of them, or I will start with cultural heritage, which is something which is less well known among the public. And in fact, we have a network in the INFN, which is called CHNet, which, if I show again the distribution of the units. Wherever you see a circle red, that means that there is an activity of concerning cultural heritage problems. And these are the basic things that we are doing. Material analysis in non-destructive ways, dating, radiocarbon, thermoluminescence, imaging techniques, computer tomography, similar to those which are used also in medicine, but applied to, not to humans, but to works of art. And we have, in particular in Florence, we have a long tradition with the analysis of materials with ion beams applied just to cultural heritage. We used a very old machine, which was too old to do still nuclear physics. And in the mid-80s of the last century, we decided to change its research goals to something else, and in particular to applications to cultural heritage. Now we have a much bigger laboratory which is dedicated to this kind of things. And of course, dealing with cultural heritage problems, we have to work in contact with scholars, and we have a lot of collaborations at national and international level with, for instance, superintendents, with museums, with the Opificio delle Pietre Dure in Florence, which is one of the most prestigious conservation institutes and restoration institutes, I would say, in the world, but also with other scientists in Italy and abroad. And here is a partial list of the collaborations we have also in Germany. And recently, among the collaborations that we have established in Italy, very important are those with the CNR. And I have seen that about this maybe Riccardo Pozzo or Luca Pezzati will talk during the round table maybe. There is this big initiative which is in a perspective of Europe, which is coordinated by CNR and in which the INFN is, I would say, well represented. It's up to you to say whether well or not, but anyway, we are represented. I go on with showing you what we do. I mean, this is the new accelerator, which is, of course, something of a completely different, on a completely different scale with respect to those monsters that have been shown by Professor Stuck now, or even smaller as compared with the accelerator at CERN. But anyway, it is a particle accelerator. It's a tandem, 3 megavolts maximum terminal voltage. This is a view of the beam lines in the target holes, people at work. And just to show you what we do, I will be very tutorial because I know that in the audience, the physicists are minority. And so, I mean, the physicists will excuse me if I'm too simple. Ion beam analysis is a kind of analysis of materials which uses particle beams, which are produced by an accelerator, sent to any object you want to analyze the composition, which can be also a work of art, and the interactions of the particles of the beam with the atoms and nuclei of the material that you hit excite atoms, nuclei, and produce the emission of radiation having characteristic energies of the atoms or nuclei that produce them, so that if you do some simple spectrometry with standard detectors of nuclear physics, you can detect the energies of these particles and be able to know which were the atoms present in the area that you have hit with your beam. That's a very simple idea, which is depicted very naively in this slide, where I have represented the different kinds of atoms in different colors. Of course, this does not mean that atoms are colored, but just to say that there may be different species present in the target, and when the beam arrives, the excitations produce emission of radiation here in the slide of the same color. That only means that it allows us to understand from where the radiation was emitted, and therefore detecting the energy, we know which were the elements present. For instance, in PIXA, which is particle-induced X-ray emission, the process this is an atom out of scale because the nucleus would be much smaller. I mean, the electrons in the orbitals. When a particle arrives and ejects an inner electron, an outer electron makes a transition to the gap which is left by in the inner orbital. And the extra energy, because it had more energy here than here, the extra energy is emitted in the form of an X-ray, which has just that energy. And since the binding energies of the electrons in the orbitals is characteristic of the atomic species, calcium, fluorine, sodium, lead, obviously also the differences, that is the energies of the X-rays, are characteristic of the elements. So this allows you to understand which is the element which emitted these X-rays. But there are other, oh my God, what happened? Troppo presto che non falliscono mai, eh? Don't send, e si ricomincia a capo. Okay. So you may have many other kinds of interactions, not only with the electrons, but also with the nucleus, producing emission of gamma rays or secondary particles, or the elastic or inelastic diffusion of the primary particles. All of this radiation can give you information about which was the target heat producing that radiation. And therefore, if you put around the target a number of detectors of the different kinds of radiation, you're able to make a very complete and multi-elemental analysis simultaneously, detecting almost all the elements in a quantitative and very sensitive way. Also trace elements are detected. And in spite of the slang that we use, we say bombard. Okay. In spite of the slang that we use when you say we bombard the target and so on, the physical conditions of the interactions, what we call the cross sections, which mean okay, so yes, I think so. The physical conditions are such that the analysis is totally non-destructive, non-invasive. You produce no damage. And you may also have information on the layer structure, which is a common case in the artifacts related to cultural heritage. You can do microanalysis, very selective in space. But this is done not just for the purpose of showing how smart are the physicists to do things that nobody is interested in. Actually, the material analysis in cultural heritage is very important for a number of reasons that I have listed there, which can go from attribution, authentication, understanding the technologies and also the materials which were used in a given period, in a given production area. You can discover that materials unavailable locally are used in a work, which means that a trade route was opened from faraway countries to import these materials, which nowadays is easy, but in the past was a much more complicated matter. You can detect deterioration processes, and also very important, the knowledge of materials is crucial before any restoration to decide the strategy and the materials to be used for the restoration, because of course you must know on which materials you are going to put your hands and your cleaning agents, for instance, to avoid making damage in the restoration rather than producing a good result. A crucial feature to perform ion beam analysis for cultural heritage is using an external beam, because of course the beam of ions are produced under high vacuum, and they are transported in high vacuum, because otherwise they would stop after the collisions in air with the residual gas. But you cannot not even think of placing a painting in vacuum, because the very fact of placing in vacuum would damage it for dehydration, for instance. And therefore, you have to extract the beam, as is done also in the hadron therapy, because also you cannot put a human in vacuum to cure a tumor. Similarly here, but we have a thin window which is strong enough to keep the pressure difference between the external environment and the vacuum, and you place your object just after the exit window, and you can place detectors and do the job that I was mentioning before. And using this kind of setup that we introduced some 30 years ago, really we have investigated, I would say, thousands of works, and with the purposes that I mentioned before. Large variety. This is just an overview of things that we have done, from manuscripts to drawings to paintings. Also relatively important. I mean, this is Vasari, this is Leonardo, this is Antonello da Messina, this is Mantegna. This is not a painting, as you see, but it is della Robbia anyway. Metal artifacts, embroideries, semi-precious stones, any kind of work, because the external beams allows you to do also large objects, provided they can be brought to the laboratory, of course, because the accelerator cannot be moved, and I will say something in a while about that. The external microbeam has been another implementation that we have done. External microbeam with a scanning capability, which through, I don't want to go into details, but with a least mode data acquisition system, which is something that I have not the time, I would say, to explain. Anyway, you can couple the energy of the radiation that you detect, which tells you which was the element present, to the position of the beam when this was created, the radiation was created. So you play with that, and you can combine this information and obtain elemental maps of gamma rays, of X-rays, also of the light, which is also emitted, visible light or UV light, which is emitted under the beam. And just to give a couple of examples, what it means, that this is an ink. You scan over this area with your microbeam. You see this is an area 2 millimeters times 2 millimeters. And if you make the map, you construct the map of iron and copper, here this means that all the iron radiation coming from iron and from copper comes from a region which is clearly correlated to the ink. If you take, for instance, calcium, you don't see this correlation, because calcium is correlated to some whitening agent in the paper. If you take sulfur, you see a correlation, but you see a larger shape, which may mean that, for instance, sulfuric radicals are spreading through the cellulose, and this is a precursor of a damage, because the acidic attack to the paper, which is responsible for the loss of so much of our archival treasure, let's say, is starting. And so, the people can start to think of how doing to prevent further damage. Another example on a painting, for instance, this is Mantegna. This is another story. For instance, the shade, the light around the pupil of the Virgin was done in gold with some background of lead tin yellow, and this part was also was an ochre. What does it mean? Well, that means that maybe the author Mantegna decided to use a precious pigment because he was depicting the Virgin. So an association of how precious the materials must be, depending also on how symbolically important is the painting. The same you see on the veil of the Virgin, which is also done in gold and the light blue area you don't see, which is around, you can detect from these maps that it is done with lapis lazuli, which is another precious pigment, whitened with some lead white. Anyway, I mean, I might show you thousands of these examples, but just to say that these things may be useful also to the historian of art. The other chapter can be dating, radiocarbon, carbon-14. Carbon-14, as you all know, is a radioactive isotope of carbon, which is formed in the high atmosphere owing to the action of the cosmic rays. And being radioactive, that means that sooner or later, with a half-life of about 6,000 years, it decays, becomes something else, disappears, dies in a sense. But it is continuously reformed so that you have an equilibrium, because those which are formed and those which decay, which produces an equilibrium concentration of about 1/10 to the 12th, 1,000 millions of carbon atoms. 1 out of 1,000 millions is billions, sorry, is radiocarbon. It oxidizes to carbon dioxide, comes to the ground level, and then is absorbed by all living organisms through metabolic processes, photosynthesis for the plants, food chain for the animals. And so every living organism has the same concentration as in atmosphere, but starting from the death of the organism, the mechanism of decay, which goes on, and is also present while we are living, but we eat and compensate those that we lose by decay by eating new fresh material containing radiocarbon. Starting from the death, we don't eat anymore, and so starting from the moment of the death, the concentration of radiocarbon with respect to total carbon decreases, and decreases following the decay rule, which is represented by this equation. But if you are not familiar with the equations, this means that if you start with a given level, please note the scale, 10 to the minus 12, and then you go down with an exponential decay. That means that if you measure how much has been left after a time t from death, you know the starting point, you know the mean life of radiocarbon, you can solve the equation and know how much time has elapsed from the death. Even if you are not familiar with the equations, this corresponds to, graphically, you measure how much is left, you know how much time has elapsed. The less is present, the longer time from death, like this. That's the principle. That's the end also. I know, there was a blank slide, just to take time. Well, all of you know that that's the key technique for dating all the finds of organic origin, because the stuff that you date once had to have belonged to a living organism for the mechanism that I show. And the date that you detect by the measurement of the concentration of radiocarbon is the time from the death of the organism of origin. So you can reconstruct absolute chronological sequences, authenticate works of art or deny authentications. You can also, that's typical of people doing radiocarbon, having some relic to be measured to see whether it's compatible or not. Every good radiocarbon laboratory must have done some relics, otherwise it is not sufficiently considered to be, of reputation. And also the way to measure radiocarbon has to do with nuclear physics, and we do that. The technique that is used is accelerator mass spectrometry. Mass spectrometry simply means that you separate the different isotopes of carbon, separate mass 14 from mass 12, and then measure the ratio, which is the key for the date. Here the principle is different from AMS, from ion beam analysis. In the ion beam analysis, your unknown was the target of a beam that you did. In the AMS, you make a beam out of the material. So you place the material in the source and extract the ions, and you accelerate the ions, most of which will be carbon-12, but some of them will be carbon-14, and then you will, after accelerating to a high energy, you are able to separate them by allowing them to pass through magnetic or electrostatic fields where the different masses make different trajectories. The reason for using an accelerator rather than a simple mass spectrometry is that you have to fight against the enemies, which are the isobars. So other things having the same mass than radiocarbon, other things having mass 14. And if you use a tandem accelerator, first of all, I mean, the first enemy is nitrogen-14. Imagine is the most abundant component of atmosphere. But the kind of sources that we use, ion sources that we use, these are negative ion sources. Well, nitrogen-14 does not produce negative ions, stable negative ions. After a very short while, they lose the extra electron. So this is a problem which is eliminated in the source. Then the mechanism, which might be complicated to explain, through which the tandem accelerator works, sees a change of charge state from negative to positive at the terminal. And this is accomplished through the interactions with the region where the vacuum is a bit worse. And during these interactions, the other two enemies, which are molecular isobars, C13H and C12H2, which also have mass 14, they are broken, the molecules, while carbon-14 has only the charge changed. And so at the end, you can make the analysis and also use extra filterings just to, better measure really only radiocarbon. That's the way it works. And you succeed in combining the huge sensitivity which is required, because the quantities that you have to measure are so small, as I mentioned, with the high precision, because any uncertainty that you get in the, in the measurement of the concentration propagates into a corresponding uncertainty in the date. If you can think also of the graphic that I showed before, and this is 1% is 80 years, so 0.5% precision is 40 years. This is the kind of results that one can obtain with accelerator mass spectrometry. We can go down to 1,000 less concentration than in a living organism, which means about 50,000 years of age, which is the limit. And also another important point is that this is not a non-destructive technique, it's a micro-destructive technique, because you need a very small quantity of material of the order of milligram or even less. Well, that's just to give you an idea of which is the sacrifice that you have to do to make the analysis. This was a relic attributed to St. Francis, for instance. This is the Artemidorus papyrus, for instance, where we cut, not we cut actually, these are not my hands, Gallazzi's, maybe some of you knows him, hands cutting with, great pain, because for them even giving 1 milligram is something, but anyway, they thought it was worthwhile. Traditionally, one has to do with applications of very old stuff. Relics, archaeology, historical finds. But the example I want to give you is not about old stuff. The idea we had was to exploit radiocarbon also to deal with contemporary art. And this can be done thanks to the bomb peak. What's a bomb peak? This is the concentration in atmosphere and in all the living organisms in equilibrium with atmosphere in the years from the last World War and in the Cold War. That's the period of the Cold War, where the Americans and the Soviet Union exploded nuclear weapons in the atmosphere, and this had the effect of almost doubling the concentration in a few years of radiocarbon in the atmosphere. You see this in these units, we are at 100 and we reached 200. Then, fortunately, they stopped with the non-proliferation treaties in the 60s, And what you see here is not the decay of radiocarbon, it's only the effect of the dilution in the oceans of the extra quantity that was put into atmosphere. But any living organism during this period bears the signature of having lived there through the presence of such a high concentration, relatively high concentration of radiocarbon. And the idea we had was to measure the supports of paintings. Of course, knowing that when you measure, for instance, the canvas age or the wood table age, you have a terminus post quem because you can always paint on an old canvas or an old piece of wood. And if you find that the age of the canvas, of the support, matches what is presumed to be the date of the painting, you cannot say that it is authentic. You only can say that it is compatible with authenticity, of course. But vice versa, it works, because if you find that the support is younger than when they say it has been painted, obviously this is impossible, because you cannot paint on a canvas which has not yet been prepared. And the first thing we did, we are doing many now, was in this painting by Fernand Léger, Contraste d'effort, one of a series of paintings that Fernand Léger had painted presumably in the 13th, 14th of the 12th century. And it was bought by Peggy Guggenheim in the late 60s for the Peggy Guggenheim Foundation in Venice. Soon after she bought, I don't know for which price, she was alerted by some historians of art that it might be doubtful because of a number of shapes or color shades that were not convincing for the art historians, but they could not say it definitely. And they were honest enough to withdraw it from the display to the public because they didn't want to show something which was suspected to be a fake. But anyway, they remained with a curiosity to know whether it was actually a fake or not. And they gave us recently a small piece, you see 1 millimeter here, of canvas, and it came out to have this concentration, 129% of modern carbon, which translated into date means that the canvas was produced using cotton plants, that was cotton, cut either in 59 or in 62, or maybe also in 79, 80, but at this time she had already the painting at home, so this was not possible. But anyway, later then when it was presumed to have been painted. Some people said, well, but Léger himself, sometimes it happens that a painter much later comes back and produces a copy of one of his own works, but this was also impossible because Léger had died before. So no doubt that was a fake. So that was, we do also not only accelerator-based techniques. For instance, I mentioned before that the main problem is the one of having a large apparatus like an accelerator, and not always you are allowed to take the works to the lab. Sometimes they do not want to do that. Sometimes it is impossible. Think of a mural painting. You cannot take it out. And so there are other techniques like XRF, which is a technique, a well-known technique which we didn't invent, but that we improved. X-ray fluorescence is similar to PIXE. Once again, you exploit the emission of characteristic X-rays. The only difference is that the induction of the emission of X-rays is produced by a beam of photons that you can obtain, for instance, from a simple X-ray tube, also a very small one. And therefore, the instrumentation can be made portable. And normally, XRF has a lot of disadvantages in comparison to PIXI because it is less sensitive to the light elements. It is less quantitative, but we made some improvements, some smart tricks, so to say, and we approached the performance of PIXI also with XRF, and then we were able to go around and make a number of important campaigns of analysis of materials with the same purposes that I mentioned before, This is Giotto, Raffaello, Beato Angelico. That's the crucifix in Santa Croce. I mean, something as tall as this room, so you might not have thought taking to the laboratory. Or this is Piero della Francesca mural painting in San Sepolcro. Now we have made some further implementations, and we have developed a scanning system which is capable of doing the same kind of thing also with XRF that I showed you before for ion beam analysis, and the possibility of having maps. We have installed permanently one of these systems, which, as you see, is much smaller than an accelerator, so it is really portable, at the opificio delle Pietre Dure. And just to show you an example, also with XRF you can have mapping and see that these parts are made in azurite, that this is lead white, and this is ochre, characterized by the presence of iron. But anyway, we have done already many tens of measurements like this in the opificio and also outside. Another technique which is used, is present in the CHNet, and we go back to dating, is luminescence. Luminescence techniques, which are performed in Milano Bicocca, in Catania, Torino, and Bari, are an ideal complement to radiocarbon because they allow to date materials, ceramics, bricks, terracotta, so inorganic materials that cannot be dated with radiocarbon. And so they ideally complement the radiocarbon capabilities, and also they are particularly suitable to detect fakes, and therefore in problems of authentication, because the response of thermoluminescence of an original Etruscan vase, for example, with a copy, you see, I mean, I have no time to enter into the explanation. That's a signal of luminescence produced by heating some materials that you take with the drill, so it's microdestructive from the material, but you immediately detect whether it is authentic or not. So it's important to do. And finally, computer tomography is, I mean, like for the humans, which is done in Bologna and Torino within the network of INFN, which allows you to make, with the computer, reconstruction of something which is inside small objects. That was a coffin, and you immediately see what is present inside, the shape without opening that. I mean, like when you see the interior of a body of a human. Also on a large scale, of course, in this case using higher X-ray energies. This is an example of that's experimental setup. Behind there is the detector, that's the X-ray source. And this is the reconstruction of the inner structure of this globe that you obtain without opening it, three-dimensional. That's really, in my opinion, I can tell it because I'm not doing personally this. In my opinion, that this is really fantastic. You can see that there are some bars that had moved, so they can decide whether intervening or not. Anyway, this is important. For the environmental monitoring, if I have 5 minutes more, two are the fields where we work. One is the aerosol composition. The aerosol, and you use ion beam analysis, X-ray fluorescence, and also radiocarbon to measure aerosols. And the other is a mapping of natural radioactivity in the air, on the soil or airborne, through extensive radiation monitoring campaigns, which are done by a group in Legnaro in particular. Atmospheric aerosol is just, is just the famous PM, the reason for giving restrictions to traffic, for instance, when you exceed a certain amount of particulate in the atmosphere. And this may have natural or anthropic origin, direct or secondary, because sometimes the emissions are gaseous and then in the atmosphere they react and then they become solid. And they have an impact of human health because you breathe them, and depending also on their size, they penetrate deeper or less deep towards the lungs. They also have an impact on climate changes because they can produce effects of shading in the radiation, so I mean what is called the radiative forcing. And though they also have an effect that I don't see anyway on the, okay, this is just the effect on the climate change you see. I mean, that's the situation in China, which is not as good as we would like to. But it may also have an impact on cultural heritage because, for instance, the black crusts on the monuments are due to the aerosol that deposit on the surface of monuments and statues. So studying aerosol is very important. You need really a huge amount of data concerning the concentration, the composition, the size, the optical properties, just to see whether they reflect or not, and also their time and space evolution, because I mean you can correlate by the evolution of in time, for instance, of the aerosol of a given composition. You can correlate or not correlate with certain industrial exhausts, for instance, or traffic or other sources. So you have to identify and quantify the emission sources to contribute to abatement of pollution in the air, and also to contribute to the models, climatic models, to evaluate, as I mentioned, the role of atmospheric aerosol in the radiative forcing problems. We also have to measure radiocarbon in aerosol because the carbon component is a large fraction of the aerosol. And the carbon component, very schematically, can be of natural, I mean, pollens, for instance, or a bad origin, for instance, the results of combustion of fossil fuels. Well, fossil fuels have no radiocarbon because they are too old. Pollens have the present concentration of radiocarbon. So if on the overall fraction of carbon you measure how much radiocarbon is present, you can see which is the fraction of natural and bad component of carbon. This is what we also do in Florence, for instance. These are examples of filters on which you have collected the particulate matter. The number means the maximum size in microns of the because I mean, as I said, the smaller the size, the deeper they penetrate. And so you collect them on filters and then simply bombard them with your beam, exactly as you do with the works of art, and obtain the concentration. You can also use samplers that allow you to have these streaks of dirt, let's say of PM, where each millimeter along this circle corresponds to the collection during 1 hour, and all the streak is 1 week. And then you place them in front of your accelerator, and millimeter by millimeter you measure the composition, and then you reconstruct the time evolution with a resolution of 1 hour, and you can discover strange things like, for instance, here in Montelupo, emission of arsenic, sodium and potassium, which are correlated to artistic glass and ceramic production. By night, typically, they emit because they want not to be seen. And once we discovered this, we told it to the ARPAT, the Agency for Regional Protection, and they probably did something to the industries. You can see also strange things like that. That is when the Italy soccer team won the World Championship, and at night that day, you have a huge amount of elements in there which are related to fireworks. This is, I mean, just an amusement, but you can see also more serious things. You can detect by multivariate statistical models which are the main sources, and you see, for instance, these are daily samples through 1 year, and you see that in winter you have a great component due to biomass burning. That's the average over the year, but in winter that's predominant in a region close to Lucca, while in other periods you have other sources which are responsible for the aerosols, and so on. And also effect of the Saharan dust, which is responsible of this effect on the cars. And this is helpful to the mayors of the cities, because you know that they are fined when in a given city you exceed the maximum limit, which is 50 micrograms of PM10 per cubic meter of air. If they exceed, if in that town this limit is exceeded more than 35 times per year, they are severely fined by the European Commission. Sometimes they are not guilty of that, because, and so, I mean, if we see that the reason for the exceeding of the limit and a number of cases was Saharan dust, they can deduct it, so, I mean, subtract it from the number of days they had been guilty, so to say, and so on. And the final thing I want to show very quickly is the radioactivity project. This is the courtesy of Fabio Mantovani, which is done mainly under the auspices of the Laboratorio Nazionale di Legnaro, which is aimed at basic research, developing also technologies. This has to do with technology transfer for the environment, and also stimulating startups to give work to young people based on know-how excellence in these nuclear technologies applied to the environmental monitoring. And you have three different approaches that you can measure in the lab after sampling on the territory. You can go in situ, and you can go on these strange vehicles, small helicopters. Each of the three approaches gives you an idea of a smaller or larger area, and uses, of course, different techniques to detect. And for instance, if you take samples, then you measure each of them in the laboratory after taking it on the territory in an automatic way. If you go to the territory, you have to measure with high efficiency detector in situ, and this can be done also including young students in these campaigns, which is also a way to approach, to have them approaching science. These are high school students doing the measurements, and they have done a lot already in three regions, in Veneto, in Tuscany, Marche, and in Sardinia. That's, I mean, a survey of what they have done. You can go on the helicopter, you follow the International Atomic Energy Agency guidelines for this kind of sampling in order to be comparable in the results with what they do in other countries. They are doing certain kinds of flights at a very small height. Well, you see this object with the equipment on, and also probably while flying, and this is just results of the area. These are not results. This shows you the results, the areas that they covered with these campaigns in Tuscany and Veneto. These are results showing you the total radioactivity in becquerel per kilogram in the various areas of Tuscany and Veneto, and in the Elba Island in particular. This is not a total radioactivity, this is just a uranium distribution, which, as you see, is concentrated in certain areas. They are not at a dangerous level, but anyway, it's well to know, to know the territory. And I think that was my end. Thank you very much.
So, please. Yeah, thank you. Very nice talk. Sometimes it's not even necessary that you know it. Sometimes it's more necessary that the other guys know that you could measure. But my question goes in the direction in miniaturizing what you did already. You think you will be within a 10-year range or so able to put the detectors on these small unmanned objects called drones, which are the last detector, which was still about this size.
These actually, I'm not so, I mean, maybe you know better than I, but because, I mean, I'm not doing directly. I think that they are going into that direction, but we probably should ask directly to them, because I might give you an answer which is not exactly informed, because...
One of your systems, they are too big, too heavy.
Which ones? I mean,
which you mentioned before, where you...
the XRF?
Yeah.
Yeah, but they are not so, I mean, in this case, for instance, the energy resolution, they use sodium iodide detectors, they do not go, they are not using solid state detectors, so they would not be suitable, I think, to do that kind of work.
More questions, please?
Thank you very much. It was very interesting. You have shown in one slide the manuscript used for the application of this technology. I was wondering whether the datation can be a result, an undated manuscript can be dated according to this technology. And another very down-to-earth question, the cost of the application of this technology.
Well, let's start from the first question. With radiocarbon, as I mentioned, the dating uncertainty at best is some tens of years, at best, because you may have other, I couldn't enter into the details, but you may have effects that increase your uncertainty. So in some cases you may even have 100 or 100 years or even more. So normally what is required for the manuscripts, it's a much more accurate dating. Indeed, indirectly, we dated documents. One of the figures I showed a manuscript by Galileo. We did a lot of measurements on Galileo's manuscripts, handwritten notes, which were not dated, and which were very interesting for a physicist. Well, it was, I mean, just a glory to study Galileo with these methods, and in particular, doing the measurements at 300 meters where he had written these notes, probably, because we were in Arcetri, so, I mean, it looked like he was there because he should have been very curious to know the results. And the idea in that case was not radiocarbon. Was a totally different idea, was the fact that at Galileo's times, the ink was homemade. And therefore, every time a batch of ink was finished and a new one prepared, it was different from the other. Not dramatic, I mean, the basic components are the same, but the quantitative ratios were different. And we made a number of measurements on dated documents, letters, for instance. And we actually saw that there were remarkable difference between a period of a few months, and then he probably had finished and then passed to a new one, where the ratios of iron to copper to zinc were totally different. And so we used this as a sort of database to compare then the ink in the undated notes. And in a number of cases, we succeeded to place the undated document by the matching to the dated letters or so. And we said, well, this must have been done in the first half of 1607, for instance. So indirectly, you can also measure. But for the traditional dating methods like radiocarbon don't work in general for that. The other question about the cost depends. I mean, most of our work is done on the basis of scientific collaborations also with the scholars. So, I mean, the product is some work that is published together and is good for AMVUR, for instance. And although not, you know what AMVUR is, but maybe
So it's the evaluation system for university productivity,
so, I mean, we are satisfied with that, but we also do third-party measurements, and just to give you an idea, but not only we, I mean, other people do, radiocarbon measurement is approximately 400 euros. The ion beam analysis, it depends on, I mean, because they never come with, make me a measurement of this point. There is always a large number of measurements to be done, and then we can bargain and decide. The order of magnitude is hundreds up to maximum a few thousands of euros.
More questions, please? Yes?
I was really impressed. These are beautiful examples for applications of atomic and nuclear physics. But what about the last step? What about commercialization? What's your viewpoint? Are you already in contact? How to make a product out of this? Are you already in contact, for example, with art dealers, or is this?
You mean about the authentication? You mean about the authentication? Whether we can be bought to say that something is authentic?
No. Somehow.
Well, actually, after we published, I mean, as usual, the first when we got the idea of the bomb peak exploitation of the bomb peak to see whether compatibility or not. We were submerged by requests of even private owners of works that were, I mean, very frightened by the fact that we might discover that it was a fake. We have done. No, that's why as you have seen, I have a tie also. I mean, that's the maximum we can do with what we earn from that. But no, this tie, by the way, is by the INFN. Look at that. Also, there is also the name. So it's not bought with the earnings of these things. But many people are asking us to do this, and we have a limited capability of doing, because doing radiocarbon measurements is, although it costs not so much, as I said, but there is a lot of work behind. And so, I mean, we decide whether to accept or not, not on the basis of a commercial earning, but on the basis of the interest that it can have. So basically, we do only these kind of things in collaboration with public institutions, not for the privates.
If I may add a point, so you may easily realize that Italian scientists, at least those of our generation, have a research and publication-directed mind, not a money-directed mind. And that's a real handicap, because anyway, anytime you present a project, the request is not what will you discover, but how much money may be done, may be made out of this project. But this a bit, maybe it's a generation handicap.
Probably. Well, unfortunately, the next generation has other handicaps.
Yes.
We will maybe discuss it.
And
also.
Environmental handicaps too.
Also.
More questions? I have one.
Yes.
I mean, when something is put into an electron microscope and just subjected to an electron beam, it is damaged. So I wonder, is it really not damaging, irradiating with high energies sample, an artistic manufacture or something like that, because part of the energy is is given to the object, and then it is dissipated again with modifications in the atomic, perhaps, or electronic structure.
That's really obviously a very good question. And at the beginning, before doing things, these kind of measurements on precious things, I don't know how many hundreds of measurements on objects that I had at home, for instance, just to see and find the appropriate conditions. But the cross sections, that is the probability of this interaction, especially for the X-ray emission, is so high that you really need very weak beams. To the physicists, I can say we use picoamperes of beam currents. And for 30 seconds or so, you have enough statistics. So in this case, really you have no damage, no visible damage. Of course, some interactions you have, because you have to interact to produce the emission of X-rays. Some materials may be more sensitive than others, insulative materials, because you implant charges. And we have seen that if you exceed certain doses of radiation, you may start to see some creation, for instance, of color centers, but they relax because, I mean, after a while, especially in the ceramics, you can see that you make a somehow darker spot after 1 minute of irradiation. But after 2 days, it had disappeared because of annealing of this effect. And if you want to accelerate it, you can heat, and a ceramic can be heated, and in a few seconds, no one will see anymore that small damage that you had produced. So the answer finally is that I am strongly convinced that they are really non-damaging. Also, the other point is that the size of areas that you investigate is very small. So, I mean, maybe in 1,000 years, the manuscripts of Galileo will be full of holes where I have put my beam. I hope not, but they will be very small holes and much smaller than the natural damage that can come from the action of ink on the paper, for instance.
Thank you. Anything more? So, thank you very much, and now it's time for the brief.